Hello there, and welcome to Physics with William, where we take difficult ideas slowly, one clear thought at a time, and allow science to be interesting without becoming noisy. Tonight, we are going to look beneath atoms, beneath particles, and even beneath the familiar idea of empty space. Our subject is quantum foam, a name that sounds as though the universe has been washing dishes, but which points toward one of the deepest problems in modern physics. Before we begin, take a moment to notice where you are. Perhaps you're lying in bed with the room nearly dark. Perhaps you're sitting beside a window, listening through headphones, or letting this play quietly while the rest of the house settles down. Wherever you are, look at the space around you. The distance between you and the wall seems calm. The air may move, dust may drift, and the building may make the occasional small noise, but space itself appears completely still. It does not fizz. It does not ripple around the furniture. It does not suddenly open a tiny doorway behind the lamp and close it again before anyone can complain. That calm appearance is one of the most dependable features of ordinary life. A table remains the same distance from the floor. A doorway keeps its shape. Light crosses a room in a predictable way. When you place a cup beside the bed, you do not expect the space under it to change its geometry during the night. You may expect the cup to be empty by morning, or perhaps mysteriously relocated by a sleepy hand, but the space around it is usually above suspicion. Physics agrees with this everyday picture over ordinary distances. The theories used to describe planets, falling objects, buildings, satellites, and light moving through the solar system treat space-time as a smooth setting. Space-time is the combined framework of space and time. It tells us where events happen, when they happen, and how one event can be connected to another. In the theory of general relativity, space-time can bend. Massive objects such as stars and planets affect its shape, and that curved shape guides the motion of matter and light. Yet even when space-time curves, it is still usually described as smooth. The curve may be gentle or severe, but it does not normally look grainy or broken. Quantum theory gives us a very different kind of picture. It describes nature at small scales, where certainty gives way to probability. A particle may not have one perfectly defined position before it is measured. A physical field cannot remain completely quiet. Even the lowest energy state is not the same as absolute stillness. Small variations remain, not because our instruments are poor, but because quantum uncertainty belongs to the theory itself. This creates a difficult question. If matter and energy follow quantum rules, and matter and energy shape space-time, should space-time also have a quantum nature? That question leads directly to quantum foam. The basic idea is not that space is literally made from bubbles. There is no cosmic detergent involved, and no enormous sponge hidden outside the observable universe. The word foam is an analogy. Imagine looking at the sea from very far above. From a high altitude, the surface may appear smooth and simple. Descend closer, and you begin to see waves. Move closer still, and you find spray, bubbles, swirling water, and rapidly changing details. The smooth surface was not exactly false. It was an accurate description at a large scale. It simply left out the fine structure that became visible when you looked more closely. Quantum foam suggests that space-time could behave in a similar way. Across the distances of daily life, and even across distances much smaller than an atom, it may look smooth, but at an unimaginably tiny scale, the geometry itself might fluctuate. Distances might not remain perfectly definite. The order and separation of events might become uncertain. The smooth setting in which physics seems to happen may turn out to be an averaged view of something far less settled. It is important to pause over the word might. Quantum foam is not an observed material, and it is not a finished theory accepted in one precise form by every physicist. It is a broad idea associated with attempts to understand quantum gravity, the still incomplete effort to describe gravity using quantum principles. Different approaches imagine the smallest structure of space-time in different ways. Some predict violent fluctuations, some predict a more restrained kind of uncertainty. Some replace the image of tiny geometric bubbles with networks, loops, strings, causal relationships, or quantum information. The shared suspicion is that the smooth space-time of general relativity may not remain smooth at every possible scale. That suspicion appears because our two greatest descriptions of nature do not fit together comfortably in the situations where both should matter. General relativity describes gravity in the large-scale structure of the universe with extraordinary success. Quantum theory describes particles, atoms, radiation, and the other fundamental interactions with equally remarkable success. Each theory has passed demanding tests. Each has helped produce technologies that now seem ordinary. Yet when physicists try to use both theories at once under extreme conditions, serious problems appear. The center of a black hole is one example. The earliest moments of the universe are another. In these settings, matter and energy can be compressed into regions where gravity is extremely strong, and quantum effects cannot be ignored. General relativity tells us that space-time is dynamic and responds to energy. Quantum theory tells us that physical quantities fluctuate and cannot always be assigned exact values. Put those lessons together, and the geometry of space-time may have to fluctuate as well. This does not mean that the floor beneath you is quietly rearranging itself in a noticeable way. Whatever quantum structure space-time may possess, it becomes relevant at a scale so small that ordinary comparisons quickly become useless. An atom is already far too large. The nucleus at the center of an atom is also far too large. Even the smaller particles studied in accelerators are examined at distances that remain enormous compared with the scale usually associated with quantum gravity. Physicists call that extreme domain the Planck scale. We will approach it carefully later, because the Planck scale is not merely a very small measurement. It marks the region where our familiar separation between quantum physics and gravity is expected to fail. For now, it's enough to picture a limit far below anything the eye can see, far below anything a microscope can reveal, and far below the internal structure of an atom. If an atom were expanded until it was larger than a galaxy, the Planck scale would still be difficult to represent fairly. The difference is so vast that almost every analogy begins confidently and then quietly gives up. And yet this inaccessible scale may be responsible for the ordinary smoothness around us. A calm surface can emerge from restless ingredients. A solid table is made from atoms in motion. Warm air is made from molecules moving in many directions. A clear tone from a musical instrument comes from countless microscopic interactions. Large-scale order does not require every small part to be motionless. It can arise because tiny variations average together. Space-time may work that way. What we experience as a stable distance could be the large-scale result of countless small quantum possibilities. What we call a location might be sharply meaningful, only after we ignore details that are too small to resolve. The steady passage of light across a room might conceal fluctuations so slight and so rapidly changing that they cancel before they can affect anything we notice. This is where the foam image becomes useful, but also where it can mislead us. Real foam exists inside space. It is made from liquid and gas. Quantum foam, if the idea is correct, would concern space and time themselves. There would be no ordinary container holding the fluctuations. The changing geometry would be the container, the distances, and the timing all at once. Asking what lies outside it would be like asking which shelf holds the idea of distance. The question uses the very concept it is trying to place somewhere. That can feel difficult because the human mind is good at imagining objects and less comfortable imagining the rules that make objects locatable. We can picture a tiny ball. We can picture a smaller ball inside it. We can continue shrinking the image until it becomes a glowing dot, although the dot usually remains suspiciously visible in our imagination. But quantum foam is not simply a collection of very small objects. It is a proposal about whether the notions of here, there, before and after remain exact when we investigate nature deeply enough. Consider an ordinary map. It uses lines, distances, and coordinates to tell you where places are. Now imagine that the paper itself refuses to stay fixed. The distance between two printed towns changes slightly each time you look. A road appears connected in one moment and separated in another. Directions remain useful across the whole country, but inside a tiny region the map becomes uncertain. That is not a literal model of quantum spacetime, but it points toward the kind of problem physicists face. They're trying to describe geometry, when geometry can no longer be treated as a silent background. Another way to approach the idea is to think about measurement. To measure a distance, you need something physical. You might use a ruler, a pulse of light, or a clock. But every ruler is made of quantum matter. Every light pulse carries energy. Every clock has physical limits. If you try to examine an extremely small region, you need a probe capable of resolving that region. A more precise probe generally requires greater concentration of energy. Gravity responds to energy, so the act of probing space-time at a tiny scale may disturb the geometry you're trying to measure. Push the process far enough, and the measurement may become self-defeating. Your attempt to inspect a smaller region could alter it so strongly that the original distance loses a clear meaning. This is one reason quantum gravity is not simply a matter of building a better microscope. A microscope normally looks at objects within space. Here, physicists are asking whether space itself has a smallest meaningful structure, an unavoidable uncertainty, or a new set of rules. The measuring instrument cannot stand outside the problem. It is made from the same universe and must obey the same limits. There is something gently humbling about that. Human beings have measured the age of ancient rocks, the motion of distant galaxies, the vibrations of atoms, and the faint radiation left from the early universe. We have placed clocks in satellites and corrected them for the effect of gravity. We have detected disturbances in space-time produced by colliding black holes. Then, at the smallest imagined scale, nature may be telling us that the idea of a perfectly marked ruler was never fundamental in the first place. Where are you listening from tonight? And what does the space around you feel like at this moment? Perhaps it feels open and quiet. Perhaps the room is small and familiar. Perhaps you're in a city apartment with traffic beyond the window, or somewhere rural where the darkness outside seems to continue for miles. You do not need to answer aloud, although you are welcome to confuse anyone nearby by announcing your location to the ceiling. Just notice how natural it feels to assume that the room has a fixed size, and that every point within it could, in principle, be measured exactly. Quantum foam asks us to test that assumption at the deepest level. It does not say that your room lacks a size. It asks whether exact distance remains meaningful without limit. It does not say that time stops working. It asks whether a perfectly definite interval can always be assigned between events. It does not say that reality becomes random nonsense. Quantum theories are highly structured and mathematically precise. The uncertainty they describe is not carelessness. It follows rules, even when those rules challenge the pictures that feel natural to us. That distinction matters. Popular descriptions sometimes turn quantum physics into a license for anything strange. A particle is uncertain, therefore perhaps thoughts control the universe. Empty space fluctuates, therefore perhaps a missing sock has entered another dimension. These are entertaining ideas, especially for the sock, but they do not follow from the science. Quantum foam is already strange enough without adding claims that the evidence does not support. The honest version is more interesting. Physicists know that general relativity is not expected to be the final quantum description of gravity. They know that quantum fields fluctuate. They know that energy and geometry are connected. They have several promising frameworks, but no complete experimentally confirmed theory showing exactly what spacetime becomes at the smallest scale. Quantum foam is one influential way of expressing the possibility that geometry loses its classical smoothness there. The name is often associated with the physicist John Wheeler, who helped develop some of the boldest ideas in 20th century gravity. Wheeler was willing to follow general relativity into regions where familiar language began to fail. He considered the possibility that at extremely small scales, space-time might undergo rapid changes not only in curvature, but even in topology, which is the basic pattern of how a space is connected. In a classical picture, a region of space has a stable arrangement. In a foamy picture, that arrangement might fluctuate, allowing fleeting structures that have no ordinary counterpart at larger scales. We should be careful not to picture these as confirmed little tunnels and bubbles popping into existence like bath foam. Such images come from attempts to translate difficult mathematics and incomplete theories into something the mind can hold. They are useful invitations, not photographs. No camera has captured quantum foam. No detector has announced that a tiny wormhole passed through the laboratory at 3:30. Researchers instead look for indirect consequences, such as minor changes in the way light travels over enormous distances, unusual noise in precise instruments, or subtle limits on how sharply space-time can be measured. So far, experiments and astronomical observations have placed limits on some proposed foam models. Certain simple versions predict effects large enough that they should already have blurred images of distant objects or altered signals in detectable ways. When those effects do not appear, the models can be restricted or rejected. Other versions remain beyond present sensitivity. This is how speculative physics becomes testable. A beautiful idea is allowed to stay only if it survives contact with observation. That process also explains why quantum foam should not be presented as a settled picture of reality. The phrase gathers several related possibilities under one memorable name. The true quantum structure of space-time, should such a structure exist, may resemble the foam imagined by Wheeler, or it may look very different. It could be discrete without being foamy. It could emerge from entanglement. It could depend on relationships rather than locations. It could reveal that space and time are not fundamental ingredients at all, but large-scale descriptions formed from something deeper. For a bedtime science journey, this may sound like dangerous material. We began with a quiet room, and now the floor of reality may not be fundamental. Still, there is no practical reason for alarm. The same universe that may contain quantum uncertainty at its smallest scale has managed to keep your bed, walls and ceiling impressively reliable. If space-time is foamy underneath, it is remarkably good at presenting a calm surface. The universe may be complicated, but it is not rude enough to make the wardrobe change distance every time you close your eyes. There is also a useful sense of scale here. Physics often describes the same thing differently at different levels. A weather map does not track every air molecule. A doctor listening to a heartbeat does not need to calculate every interaction inside every cell. An engineer designing a bridge does not begin with quantum field theory. The larger description is not wrong because a deeper description exists. It is the correct tool for the scale in question. In the same way, smooth space-time can remain an excellent description, even if it emerges from quantum structure. General relativity may be like a map that becomes accurate when we stand far enough back. Quantum gravity would explain why that map works, where it stops working, and what replaces it when the scale becomes too small for ordinary geometry. This leads to the central question we will keep returning to. What is quantum foam, really? Is it a literal turbulence of space-time geometry? Is it a shorthand for unavoidable uncertainty in distance and duration? Is it a collection of tiny changes in topology? Is it an early clue from a period when physicists had not yet found the better language? Or is it pointing toward a genuine layer of reality that remains hidden, because no present experiment can resolve it directly? The careful answer is that we do not yet know, but we know enough to make the question precise. We can trace why it arises. We can understand the scale at which it becomes relevant. We can examine the proposals it inspired and the observations designed to test them. We can separate what is established from what is possible, and what is possible from what is merely convenient to imagine. That is the route we will take. We will begin with the smooth space-time of ordinary physics and slowly reduce the scale. We will see why quantum theory refuses to permit perfect stillness. We will meet the Planck scale, where familiar measurements reach their conceptual limit. We will look at the original picture proposed by Wheeler, at tiny changes in geometry, at possible wormholes and virtual black holes, and at the much larger problem of bringing quantum theory and gravity into a single framework. Later, we will ask whether distant light, sensitive interferometers, or other experiments could reveal any trace of the foam. If you find this kind of slow investigation relaxing, you can support the channel with a like and a subscription. It helps these long, quiet discussions reach people who enjoy learning without being hurried. You might also leave a comment with where you're listening from, or with the time in your part of the world. There is something appropriate about people in different places under different skies, listening together to a question about whether place and time remain exact all the way down. For now, let your attention rest on the simple space around you. It looks continuous. It feels stable. A line from one side of the room to the other seems as though it could be divided again and again, each smaller distance still part of the same smooth whole. That assumption has served physics extremely well. It guides rulers, clocks, maps, orbits, and the paths of light. But the closer we try to look, the more difficult the assumption becomes to defend. Quantum uncertainty enters the measurement. Energy begins to disturb the region being examined. Gravity can no longer be left outside the calculation. The smooth background starts to participate in the experiment, and the idea of an exact location becomes less secure. So we will move inward carefully, beginning with the surface that appears calm and asking what happens when space-time itself is no longer allowed to remain perfectly still. That apparent stillness is the first thing we need to examine. Space looks calm because, at the scale of rooms, streets, planets, and even atoms, the changes predicted by quantum gravity would be far too small to notice. A ruler placed on a desk keeps the same length. A beam of light travels across the room without becoming confused about where the opposite wall is. Two clocks sitting beside each other can be compared without either one suddenly deciding that Tuesday has become optional. All of this encourages us to treat space-time as a smooth and dependable background. In general relativity, however, space-time is not merely an empty stage. It has geometry. That geometry determines distances, durations, and the paths followed by freely moving objects. Matter and energy affect the geometry, and the geometry affects matter and energy in return. A star changes the space-time around it. A planet follows a path through that curved region. Light also follows the geometry, which is why a massive object can bend the path of a light ray. The important word here is smooth. In the classical description, the curvature of space-time can vary from place to place, but it varies continuously. There are no sudden missing pieces between one point and the next. If the gravitational field changes across a region, we can imagine measuring that change at smaller and smaller intervals. The details may become complicated, but the underlying geometry remains well behaved. Smooth does not mean flat. The surface of a large hill is smooth even though it is curved. A sheet can bend without becoming rough. General relativity allows space-time to stretch, curve and carry waves, while still treating it as a continuous geometry. This distinction matters because physicists have already observed space-time changing. Gravitational waves produced by violent events such as merging black holes travel through the universe and alter distances by very small amounts. They show that space-time is dynamic. They do not by themselves show that space-time is quantum or foamy. A gravitational wave is an organized disturbance with a clear large-scale pattern. Quantum foam would involve uncertainty in the geometry at extremely small scales. Comparing the two is rather like comparing a slow swell moving across the ocean with the restless detail found among bubbles at the surface. Both involve change, but they belong to very different scales and require different descriptions. To understand why physicists expect any small-scale trembling at all, we have to turn to quantum theory. Quantum theory does not permit every physical system to settle into perfect stillness. Even when a system has the lowest energy it's allowed to have, some uncertainty remains. Position and motion cannot both be fixed with unlimited precision. Fields cannot be assigned perfectly definite values everywhere. The quietest state allowed by quantum physics is not the same as a classical state in which absolutely nothing happens. A simple mechanical picture can help. Imagine a small weight attached to a spring. In classical physics, you could place the weight at the exact resting point and leave it there with no motion. It would have a definite position and no speed. In quantum physics, that perfectly motionless state is not available. Confining the weight to an exact position would make its motion highly uncertain. Eliminating all motion would make its position uncertain. The lowest energy state therefore retains a small amount of unavoidable activity. Real quantum fields are not tiny weights on springs, but each possible pattern of a field behaves in a related way. The electromagnetic field, for example, has a lowest energy state that we call the vacuum. That vacuum is not ordinary empty nothingness. It is the lowest energy condition of the field, and it still contains quantum uncertainty. Measurements made under carefully controlled conditions can reveal effects associated with this vacuum structure. It is common to explain the quantum vacuum by saying that particles are constantly appearing and disappearing. That phrase can be useful, but it is easy to take too literally. The deeper statement is that quantum fields have fluctuations and uncertain values even in their lowest energy states. The particles used in calculations are one way of describing interactions. We should not imagine empty space as a crowded waiting room where fully formed particles repeatedly enter. Notice there are no available chairs, and leave before anyone records their names. The vacuum can still have physical consequences. It can affect the forces between closely placed objects. It can shift energy levels in atoms. It influences how particles interact. These effects tell us that the quantum vacuum has structure, even though it does not behave like an ordinary material filling space. Now gravity enters the problem. In general relativity, gravity is the geometry of spacetime. In quantum physics, physical fields fluctuate. If gravity is also a quantum field, then the quantities describing spacetime geometry should not remain perfectly definite. The shape of spacetime should have quantum uncertainty. This is the basic route from ordinary quantum fluctuations to the idea of trembling spacetime. It does not require us to assume that space is literally shaking like a loose window in the wind. The uncertainty may concern measurable distances, durations, curvature, and the relationships between events. A classical geometry assigns these properties definite values. A quantum geometry may instead assign a range of possible outcomes, with different probabilities, until a physical interaction or measurement makes one result relevant. John Wheeler's original work on quantum geometrodynamics argued that gravitational fluctuations could have qualitatively new consequences at the extremely small scale where quantum gravity becomes important. There is a complication hidden in the word geometry. Other quantum fields live in spacetime. Their changes are described at locations and moments that spacetime helps define. Gravity is different because the gravitational field determines the structure used to describe location and time in the first place. Quantizing gravity therefore means quantizing part of the framework on which the usual quantum description depends. Suppose you want to describe an electron moving through a laboratory. You can define the laboratory coordinates, specify the time, and calculate the probability of finding the electron in different places. The spacetime background is treated as fixed enough for the calculation, but if the background itself becomes quantum uncertain, then the meaning of those places and times may also become uncertain. It's no longer enough to ask where the electron is. You may also have to ask what kind of geometry makes the word where meaningful in that situation. This is one reason quantum gravity has resisted a simple solution. It is not merely another force waiting to be added to a list. The other fields can usually be described against a background of space and time. Gravity is tied to the background itself. When it becomes quantum, the stage joins the actors, takes part in the scene, and may move the furniture while the calculation is still being performed. At ordinary energies, this difficulty can be controlled. Physicists can treat small disturbances of spacetime as quantum excitations moving on an approximately fixed background. In that approach, the quantum unit of the gravitational field is called a graviton. No individual graviton has been directly detected, and doing so would be extraordinarily difficult, but the concept is useful in calculations. At low enough energies, gravity can be handled as an effective quantum theory without requiring a complete account of the deeper structure of spacetime. An effective theory is not a guess with better clothing. It is a systematic description designed for a particular range of scales. Fluid mechanics is effective even though water is made from molecules. Classical gravity is effective even if spacetime has a quantum foundation. A theory does not have to describe every possible scale to produce precise and reliable predictions within the domain where it applies. Quantum general relativity can be treated consistently as an effective field theory at ordinary energies, while leaving the unknown high-energy structure for a more complete theory to explain. Trouble develops when we try to examine shorter distances and higher energies. Quantum effects become harder to ignore, while the gravitational effect of concentrated energy becomes stronger. The two theories begin to interfere with the assumptions each one normally uses. Consider how a distance might be measured. You could place a clock at one location, send a pulse of light toward a mirror, and record how long the pulse takes to return. From the travel time, you infer the distance. This sounds simple, and for ordinary distances it is. Yet the clock and mirror are physical objects. They have mass, size, and quantum uncertainty. The clock cannot have a perfectly definite position. If it moves during the measurement, the inferred distance changes. You might try to reduce that uncertainty by using a heavier clock. A more massive object is generally easier to keep localized, but adding mass also strengthens gravity. Concentrating too much mass and energy into a very small region changes the space-time you're attempting to measure. At an extreme limit, the measuring device could interfere so strongly with the region that the idea of a passive measurement collapses completely. The light pulse creates a similar problem. To resolve a smaller distance, you need radiation with a shorter wavelength. Shorter wavelengths require higher energy. Pack enough energy into a sufficiently small region, and its gravitational influence can no longer be neglected. The probe begins to reshape the object of the measurement. This does not establish one universally agreed smallest distance. Different arguments and different candidate theories lead to different details. It does show why unlimited resolution cannot be assumed without question. At some point, quantum uncertainty and gravitational backreaction become part of the same problem. The microscope, the ruler, the clock, and the geometry can no longer be treated as separate pieces. The term backreaction simply means that the thing doing the probing affects the system being probed. This happens in ordinary situations too. A thermometer absorbs or releases a small amount of heat when placed in a cup. Usually the effect is negligible. At the scale relevant to quantum gravity, the gravitational response of the measuring energy may be central rather than negligible. There is another path to the same conclusion. Matter fields fluctuate, and matter contributes to gravity. Even a quantum state with a well-defined average energy can have variations around that average. If spacetime responds only to the average, some information about those variations is lost. If it responds to the full quantum behavior, the geometry itself must take part in a quantum description. Physicists often begin with semi-classical gravity, where matter is treated quantum mechanically while spacetime remains classical. The classical geometry responds to the average influence of the quantum matter. This approximation is useful in many situations, including important work on black holes and the early universe. But it is not expected to be complete. When fluctuations become large, an average can hide exactly the behavior we need to understand. Imagine a person who spends half the day in one city and half in another. Their average position might lie in a field between the two, but that does not mean they spent lunch sitting among the crops. Averages are useful, but they do not always describe the underlying alternatives. In the same way, an average distribution of quantum energy may produce a smooth, classical geometry, while concealing strong variations in the actual quantum state. If the geometry responds differently to different possible energy arrangements, then space-time and matter can become linked. One possible geometry accompanies one possible distribution of matter, while another geometry accompanies another. The combined state cannot always be separated into a definite space-time and a quantum system placed inside it. Matter and geometry may be entangled. Entanglement means that the physical description of one part cannot be completed independently of the other. It does not provide instant messaging, secret telepathy, or a convenient excuse for forgetting to reply to an email. It means that the possible measurement outcomes are correlated in a way that has no ordinary classical equivalent. In quantum gravity, such correlations may exist between matter and the geometry through which matter moves. At large scales, all of these possibilities have to produce the stable world we observe. The chair does not occupy several visibly different geometries. The clock on the wall does not report a spread of incompatible times. Interactions with the surrounding environment rapidly suppress observable interference between large-scale alternatives. The result is an effectively classical world with a geometry that appears definite. The smoothness may therefore be statistical. A room contains an enormous number of air molecules moving in different directions. We do not track them individually. We describe pressure and temperature, which remain stable enough to measure. Smooth spacetime could similarly be a large-scale description that ignores microscopic quantum details. The analogy has limits. We know what air molecules are and how their motion creates pressure. We do not yet know the fundamental ingredients, if any, from which spacetime emerges. They may not be objects moving through a deeper space. Space itself may arise from relationships among quantum degrees of freedom. Asking where those ingredients are located could be meaningless, because location would be one of the properties they collectively produce. This is where ordinary language begins to cause trouble. Saying that spacetime trembles makes it sound as though spacetime has a position and moves around inside something larger. That is not what is meant. There is no confirmed outer room in which our spacetime shakes. The trembling refers to changes or uncertainty in the internal geometry. Distances between events can fluctuate. Curvature can fluctuate. The connection between neighbouring regions may fluctuate. The rules used to compare clocks and rulers may no longer produce one exact classical answer. Even the phrase small scale must be handled carefully. We normally define a scale by measuring a distance, but the distance itself may be uncertain. Physicists can still use operational definitions based on the energy of a probe or the behaviour of physical clocks and light signals. The point is that the familiar idea of zooming into a fixed background may stop working. We are not merely looking at smaller objects. We are testing whether the measuring grid remains intact. One way to see the difference is to compare a photograph with the surface on which it is printed. If you enlarge an ordinary photograph, individual pixels may appear. The image becomes rough because the recording medium has discrete elements. Quantum space-time could have a smallest unit, but it does not have to resemble a digital image. Some theories predict discrete areas or volumes, others retain continuous variables while changing their quantum relationships. Still others suggest that geometry emerges from more basic information. Foam is one possibility among several, not the automatic result of magnification. The trembling also need not have one universal strength. Different models predict different ways for uncertainty to accumulate. In some pictures, tiny fluctuations partly cancel over long distances. In others, they could build up like a random sequence of small errors. Certain proposals predict that light travelling across the universe might carry a trace of the underlying irregularity. The arrival times, phases, or directions of photons could be altered by extremely small amounts. Astronomers have used sharp images of distant objects and precisely timed signals to test some of these ideas. If space-time produced too much random disturbance, light from very distant sources would lose its clean structure before reaching us. The fact that distant images can remain sharp places strong limits on simple foam models that predict large cumulative blurring. This does not rule out quantum spacetime, it rules out particular ways in which the effect might grow. Analyses using distant quasars and high-energy observations have excluded several proposed models, while leaving the broader question of quantum spacetime unresolved. Laboratory experiments also search for unexplained noise in precise measurements of position. Interferometers compare paths taken by light and can detect changes far smaller than the width of an atomic nucleus. These instruments were developed for purposes such as detecting gravitational waves, but they can also test proposed forms of quantum geometric uncertainty. No accepted observation has yet revealed quantum foam. The measurements instead narrow the range of possibilities and force theoretical models to become more careful. The Fermilab holometer, for example, tested particular models of correlated quantum geometrical noise and placed constraints on them without claiming a general detection of quantum spacetime. This absence of direct evidence should remain part of the story. The idea is motivated by a serious conflict between successful theories, not by a confirmed image of bubbling spacetime. Physicists expect that gravity must eventually receive a quantum description, but expectation is not observation. The exact nature of that description remains open. There are also reasons the effect may be much quieter than the name foam suggests. The smaller scale could be highly quantum, without producing violent disturbances at larger distances. Quantum alternatives can combine in ways that preserve symmetries and suppress observable deviations. A surface can be built from discrete atoms and still reflect a clear image. A sound can come from individual molecular collisions and still reach the ear as a steady note. Microscopic complexity does not guarantee macroscopic disorder. General relativity itself encourages caution. At any ordinary point in space-time, a freely falling observer can choose a sufficiently small local region where gravity appears weak and the laws of special relativity work very well. This local smoothness is one of the theory's central features. A quantum theory of gravity must recover it wherever quantum geometric effects are negligible. The foam, if it exists, cannot simply destroy the successful structure we already know. Instead, smooth spacetime should emerge as the average or large-scale limit of the deeper theory. The new description has to explain why distances are stable, why clocks agree when corrected for known relativistic effects, why light follows predictable paths, and why gravitational waves behave as general relativity predicts. It must add quantum structure without turning ordinary navigation into a weakly experiment. This requirement is stronger than merely inventing an interesting microscopic picture. Many different models can be imagined. Far fewer can reproduce the precision of known physics. A successful theory must be strange at the scale where strangeness is required, and comfortably ordinary everywhere else. As we move toward that scale, our language shifts. We stop asking only how much space-time is curved and begin asking how sharply curvature can be defined. We stop assuming that every distance has an exact value and begin asking for the probabilities of different measurements. We stop placing quantum fields on one fixed geometry and consider states in which matter and geometry vary together. The smooth surface has not vanished. It remains the correct description of almost everything we directly experience. What changes is our confidence that the smoothness continues without limit. Quantum theory tells us that perfect stillness is usually an idealization. Gravity tells us that energy and geometry cannot be separated. Measurement tells us that sharper probes require stronger disturbances. Taken together, these clues suggest that there is a domain where spacetime can no longer behave like a silent, continuous background. Finding the location of that domain requires a special set of natural scales. They are built from the basic constants that govern quantum effects, gravity, and the speed at which information travels. When those ingredients are combined, they point to distances and durations so small that our everyday vocabulary has almost nothing useful to compare them with. That is where the smooth geometry begins to lose its classical certainty. It is also where the word foam becomes more than a loose image. because the expected fluctuations are no longer tiny corrections on a stable background. They may become as important as the background itself. To understand why physicists place this change at one particular range, we need to approach the Planck scale and ask what a smallest meaningful distance could actually mean. That range is known as the Planck scale, and it is where our usual descriptions of space, time, matter and gravity are expected to stop working independently of one another. The name can make it sound like a physical layer waiting beneath everything else, rather like the final board under a stack of floorboards. That picture is too definite. The Planck scale is first of all a set of natural units. It tells us where several basic features of physics become equally important. Whether it is also a genuine smallest size is a deeper question that remains open. The story began with Max Planck near the end of the 19th century. Planck noticed that a small group of universal constants could be combined to define units that did not depend on the size of the Earth, the length of a king's arm, or the motion of a particular planet. One constant describes the strength of gravity, another belongs to quantum physics and sets the scale at which quantum effects appear. A third is the speed of light, which connects space and time and places a limit on how quickly information can travel. These constants come from very different parts of physics. Gravity governs falling objects, planets, stars, and the overall structure of the universe. The quantum constant governs atoms, particles, and the uncertainty built into microscopic systems. The speed of light is central to relativity and to the causal structure of spacetime. When all three are combined, they produce a length, a time, a mass, a temperature, and other related quantities. These are called Planck units. Planck introduced the idea before either quantum mechanics or general relativity existed in their modern forms. He was interested in a universal system of measurement. He was not announcing that space had been discovered to contain tiny blocks. The later importance of the units came from developments that Planck could not yet have seen. Once physicists understood quantum theory and Einstein's description of gravity, the Planck units began to look like signposts pointing toward the place where the two theories must interact directly. The Planck length is about 1.6 times 10 to the power of negative 35 meters. That number is difficult to hold in the imagination because ordinary objects provide no useful comparison. A proton is already extremely small, with a size around 1/1,000,000th of 1/1000,000th of a meter. The Planck length is about 20 orders of magnitude smaller than that. A concrete enlargement may help. Imagine increasing everything until one Planck length became 1 millimeter, about the thickness of a small coin. On the same scale, a proton would be several light-years across. Light would need years to travel from one side of that enlarged proton to the other. The gap between the proton scale and the Planck scale is therefore not a minor step below known particle physics. It is an enormous unexplored interval. The Planck time is the time light would take to travel one Planck length in empty space. It is about 5.4 times 10 to the power of negative 44 seconds. Calling it the shortest possible moment would go beyond what has been established. It is better to say that it marks the duration at which the familiar separation between quantum theory and gravity is expected to become unreliable. The Planck mass is surprising for the opposite reason. It is not extraordinarily tiny by everyday microscopic standards. It is about 22 micrograms, roughly in the range of a very small visible speck. That seems completely out of place beside a length far smaller than a proton. The reason is that the Planck mass represents a large amount of energy when concentrated into the tiny region associated with the Planck scale. For an elementary particle, the Planck mass is a stenosmus. The particles studied in accelerators have masses far below it. Reaching the Planck energy in a single controlled collision would require technology far beyond anything currently available. This practical barrier is one reason quantum gravity has developed mainly through mathematics, consistency arguments, astronomical observations, and indirect experimental tests. The Planck scale appears because gravity becomes stronger relative to quantum effects as energy is concentrated into a smaller region. Gravity seems weak in daily life. A small magnet can lift a metal object against the gravitational pull of the entire Earth. At the level of ordinary particles, gravity is also much weaker than the other known interactions. But this comparison changes when enough energy is compressed into a sufficiently small volume. Quantum physics tells us that examining shorter distances requires probes with shorter wavelengths. A shorter wavelength means a higher energy. That principle has driven much of particle physics. To investigate finer structure, researchers build machines that accelerate particles to greater energies and collide them. The collision energy can reveal details that lower energy probes cannot resolve. If gravity did not respond to energy, this process could continue without a conceptual limit. We could imagine using more energetic probes to examine smaller and smaller regions. General relativity changes the situation. Energy affects space-time. A highly energetic probe does not simply look at a region, it contributes to the gravitational field of that region. At first, the contribution is negligible. Increase the energy and reduce the region far enough, however, and the gravitational disturbance becomes significant. The attempt to improve the measurement begins to alter the geometry being measured. In many thought experiments, continuing the process leads to the possibility that the concentrated energy would form a black hole. The region would then be hidden behind a horizon, preventing the probe from returning the information that was supposed to improve the measurement. This argument is often summarized by saying that trying to see below the Planck length creates a black hole. It should be treated as a useful physical warning rather than a completed proof. The reasoning combines quantum ideas with classical general relativity, precisely where both theories may need to be replaced. A correct quantum theory of gravity might change the details. Even so, the argument shows why the problem is different from ordinary limits in engineering. More energy does not necessarily produce more information forever. Beyond some point, more energy may produce more gravity instead. There is another way to state the problem. A particle used to probe a tiny region has a quantum wavelength. To confine that particle more tightly, its momentum must become less certain, and its typical energy must rise. At the same time, every form of energy gravitates. Quantum theory pushes the energy upward, while gravity changes the region in response. The Planck scale is where neither effect can be ignored. This is why the scale is often described as the meeting point of quantum physics and gravity. The phrase does not mean that quantum effects suddenly switch on at one exact distance. Quantum behavior is present at much larger distances, and gravity is present everywhere. It means that near the Planck scale, the quantum nature of matter and the gravitational nature of space-time are expected to influence one another with comparable importance. The word scale also allows some flexibility. The exact onset of new physics might not occur at precisely one Planck length. A complete theory could introduce numerical factors, additional dimensions, new particles, or other structures that shift the relevant distance. Some proposals place important quantum gravity effects somewhat above or below the simplest Planck estimate. The Planck length is therefore best treated as an order of magnitude guide rather than a border marked by a tiny sign. It is also essential to separate a minimum measurable length from a smallest piece of space. These ideas sound similar but are not identical. A minimum measurable length would mean that no physical procedure could distinguish distances below a certain resolution. Space might still be mathematically continuous beneath that limit. A smallest piece of space would mean that geometry itself comes in indivisible units. A third possibility is that distance ceases to be fundamental and emerges only at larger scales from more basic relationships. Consider the resolution of a photograph. A blurred image may prevent you from distinguishing details below a certain size, even though the photographed object is not made from patches of blur. The limitation belongs to the measurement. A digital screen is different. Its image is built from actual pixels. Then consider a network in which only connections matter and no underlying surface exists at all. A smooth image might emerge from the network without being made from ordinary pixels. Quantum gravity includes versions of all three broad possibilities. Some candidate theories do predict discrete geometric quantities. In loop quantum gravity, for example, areas and volumes can have discrete spectra. This does not mean space is a simple cubic grid. The geometric units are associated with quantum states and networks, and their behavior is more complicated than a set of identical blocks arranged in rows. String theory approaches the issue differently. Its basic objects are extended rather than point-like. When energy is added to a string in an attempt to probe a shorter distance, the string can spread or excite additional modes. In many string-based arguments, this leads to an effective limit on spatial resolution related to the string scale, which is often close to the Planck scale but need not be exactly the same. Other approaches describe spacetime using causal relations, quantum information, non-commuting coordinates, or a continuous geometry whose behavior changes at very high energy. Not every approach requires literal discreteness. Some allow distances smaller than the Planck length in the mathematics, while denying that those distances can be independently measured. Others suggest that the concept of distance is replaced by a different description before such questions arise. This variety is the reason careful physicists avoid saying that the Planck length is definitely the smallest possible length. It is a strong expectation in many approaches, but the meaning of minimum can vary. It may refer to the smallest measurable separation, the smallest eigenvalue of a geometric quantity, the shortest useful wavelength, the size of an extended fundamental object, or the point where ordinary space-time language fails. A naive pixel picture creates another problem. If space were a fixed grid of tiny cubes, an observer moving relative to the grid might see the cells distorted. That could reveal a preferred state of rest, conflicting with the principle that the laws of physics should take the same form for observers moving at constant speed. Relativity has survived extremely precise tests, so any discrete theory of space-time must recover its symmetries or explain why violations are too small to observe. This does not make discreteness impossible. A quantum structure can preserve relativity in ways that an ordinary stationary lattice cannot. The lesson is simply that the smallest scale cannot be understood by shrinking familiar building materials. Tiny bricks would still sit in space, occupy positions and define a background. A theory of quantum space-time has to explain the background itself. Time creates a related difficulty. If the Planck time were a universal tick shared by the entire universe, it could introduce an absolute clock, which relativity does not permit. Different observers can disagree about durations and simultaneity, while still agreeing on the laws of physics. Any fundamental temporal structure must fit that fact. It cannot simply turn the universe into a film that advances through identical frames for everyone at once. The Planck time is therefore not confirmed to be the refresh rate of reality. There is no evidence that the universe pauses between moments or updates itself in synchronized steps. The value is a natural unit derived from the constants, and it indicates a regime where our usual concept of duration may need revision. Something similar applies to the Planck temperature. It is an enormous temperature associated with particles carrying Planck scale energies. Conditions near this range may have existed in the earliest stages of the universe, though our current theories cannot describe the earliest interval with confidence. Reconstructing the past eventually requires extrapolating toward energies where quantum gravity becomes unavoidable. Cosmologists can describe the universe very successfully from a tiny fraction of a second after its earliest known phases. As the description is pushed further back, matter becomes hotter and denser. Quantum fields dominate, and space-time curvature can become extreme. Near the Planck era, classical general relativity is no longer expected to provide a complete account. Statements about what happened before or during that regime depend on an unfinished theory. This is one reason the Planck scale matters, even though we cannot reach it in a laboratory. The universe may have reached it for us. The earliest cosmic conditions could have left indirect traces in later structures, radiation, or gravitational waves. Finding such a trace would be difficult because subsequent evolution can erase or disguise the original signal. Still, cosmology gives physicists a natural setting in which Planck scale processes might have occurred. Black holes provide another setting. Far from a black hole, general relativity gives an excellent description. Near the horizon of a large black hole, the local curvature can remain modest, and an observer falling through may notice nothing abrupt at that location. But deeper questions about evaporation, information, and the final state of the black hole lead toward very small scales and high energies. Near the classical singularity, the theory predicts that curvature grows without limit. Most physicists interpret that result not as a reliable picture of an actual point with infinite density, but as evidence that the classical description has been pushed beyond its range. The Planck scale marks where a replacement is expected. The singularity might be removed, spread out, bounced, or replaced by a quantum state, with no classical geometric interpretation. Different theories give different answers. What they share is the expectation that ordinary smooth spacetime cannot be trusted all the way to the classical endpoint. There is an important contrast between the Planck scale and the smallest distances already tested. Particle experiments have examined matter at scales vastly larger than the Planck length, and found particles that behave as point-like within current resolution. This does not mean those particles have been shown to possess literally zero size. It means no internal structure has been detected down to the experimental limit. The remaining gap is so large that direct extrapolation becomes risky. There could be undiscovered physics between present experiments and quantum gravity. New symmetries, particles, dimensions, or interactions could alter the route. The Planck scale is not necessarily the next stop after the standard model. It is the scale at which our present concepts give us strong reasons to expect a major change, even if other changes occur first. Because direct access is difficult, theoretical consistency plays an unusually large role. A candidate theory must reproduce general relativity at large scales. It must respect the successful principles of quantum theory. It should explain black hole thermodynamics, or at least fit what is known about it. It should avoid uncontrolled infinities and produce results that do not depend on arbitrary choices. Ideally, it should also make predictions that distinguish it from competing approaches. This is a demanding list. It explains why no single theory has yet earned universal acceptance as the confirmed description of the Planck scale. The mathematics is difficult, but the conceptual problem is just as serious. Space and time are used to formulate ordinary physics. Replacing them means finding a new language from which familiar space-time can emerge. The difficulty can be compared with trying to describe water without assuming wetness, flow, or a continuous surface. Molecular theory succeeds because it replaces those large-scale properties with particles and interactions, then explains how the familiar behavior emerges. Quantum gravity must do something similar for geometry, except its fundamental ingredients cannot simply move through an already existing space and time. If they did, the explanation would assume the very structure it was meant to derive. This is why the phrase smallest stage can be misleading. A stage is already a place. It has dimensions and a background on which events occur. At the Planck scale, place and duration may be among the things that require explanation. The deeper theory might not describe smaller objects inside spacetime. It might describe the conditions from which spacetime becomes possible. Even so, the Planck units give researchers a practical target. They identify combinations of gravity, quantum physics, and relativity that no theory can ignore. They guide estimates. They help compare different models. They indicate why quantum gravity effects are normally weak, and why extreme conditions are required to reveal them. At distances much larger than the Planck length, small quantum geometric effects should average out or become suppressed. Smooth spacetime then reappears just as the continuous behavior of a liquid appears when individual molecules are not resolved. The analogy cannot tell us what the underlying ingredients are, but it shows how a theory can contain microscopic structure without making the ordinary world visibly rough. Near the Planck scale, that averaging may fail. Curvature fluctuations could become large. Different geometries could contribute to the same quantum process. The topology of a region might no longer remain fixed. A distinction between one path and another could become uncertain. Even the number of meaningful locations in a region might depend on the quantum state. Those possibilities led John Wheeler to ask what space-time would look like if it were examined at the scale where quantum uncertainty and gravity meet. He did not picture a neat array of permanent cells. He pictured geometry becoming active, irregular, and capable of rapid change. The calm space-time used in classical physics would then be the large-scale appearance of a much less settled quantum structure. The Planck scale provided the size of the arena, but not the rules operating within it. To describe those rules, Wheeler reached for an image that was simple enough to remember and strange enough to signal that ordinary geometry had been left behind. That image was space-time foam. The image of foamy space-time did not appear because someone happened to think that bubbles sounded interesting. It grew from a serious attempt to understand whether matter, energy, and even particles could be explained through geometry. The physicist most closely connected with this attempt was John Archibald Wheeler, an American researcher whose work moved through nuclear physics, gravity, black holes, quantum theory, and some of the most difficult questions about the structure of reality. Wheeler had a habit of taking problems that already seemed strange and pushing them one step further. He did not treat unusual consequences as reasons to retreat from a theory. He treated them as clues. When the mathematics of general relativity suggested that space could bend, Wheeler wanted to know how far that bending could go. When quantum theory suggested that physical quantities could fluctuate, he asked whether the geometry of space could fluctuate as well. When other physicists treated empty space as a background, he wondered whether the background might be able to produce structures that looked like matter. This way of working was important, because gravity was not a fashionable area of physics during much of Wheeler's early career. General relativity had already changed the understanding of space and time, but many researchers considered it distant from the experimental and technological advances taking place elsewhere. Quantum mechanics was explaining atoms, nuclear physics was developing rapidly, particle experiments were revealing new members of what was becoming a very crowded microscopic family. General relativity, by comparison, could appear quiet and isolated. Wheeler did not see it that way. He believed Einstein's theory still contained ideas that had not been fully explored. General relativity said that gravity was not an invisible pull acting through a passive space. Gravity was the shape of space-time. Matter affected that shape, and the shape guided the motion of matter. Once this idea was taken seriously, a more ambitious question followed. Could the things normally placed inside space-time also be understood as structures of space-time? This was not an entirely new ambition. Einstein and other physicists had searched for unified field theories that could describe gravity and electromagnetism within one geometric framework. Wheeler approached the goal with his own methods and language. He became interested in what he called geometrodynamics, a program that treated the changing geometry of space as a central physical object. The name was chosen carefully. Geometry usually brings to mind fixed shapes, lines, and surfaces. Dynamics concerns motion and change. Geometrodynamics joined the two. Geometry was not fixed. It could evolve. It could carry waves. It could respond to energy. In Wheeler's program, the geometry might even form stable or partly stable structures that behaved like physical objects. One of his early examples was the geon. The word combined parts of gravitational and electromagnetic. Wheeler asked whether a bundle of electromagnetic radiation could be held together by the gravity created by its own energy. Light carries energy, and energy contributes to gravity. If enough radiation were arranged in the right way, perhaps its gravitational field could keep the radiation confined for a long time. The result would not be a particle made from ordinary material. It would be a concentration of fields and curved geometry. Radiation would help produce the gravitational structure that trapped the radiation. The object would be held together by its own physical effects, like a conversation so interesting that it prevents everyone involved from leaving the room. Wheeler analysed such objects using classical general relativity. He found that geon-like configurations could be considered, although they would not provide simple permanent replacements for elementary particles. They could lose energy and change over time. Their stability was limited. Even so, the idea demonstrated something important. Empty space governed by fields and geometry could possess complicated self-organized structures. A physical object did not always have to begin as a small, hard piece of material. This fitted a broader hope that properties associated with matter might arise from geometry. Mass could appear because energy curves space-time. Electric charge might be connected with unusual patterns in electromagnetic fields and the way space was connected. What looked like a particle from far away might turn out, on closer examination, to be a feature of geometry. The attraction of this program is easy to understand. Physics had accumulated a growing list of particles, each carrying properties such as mass, charge, and spin. A theory that simply accepted every property as a separate basic fact felt incomplete. Wheeler wanted to know whether several of these facts could emerge from one deeper structure. It was rather like entering a room filled with many different clocks and discovering that they were all driven by one mechanism behind the wall. The clocks might look different and show different information, but their apparent variety would come from a shared source. For Wheeler, geometry was a candidate for that source. The proposal also had a practical scientific purpose. A geometric model could avoid the troublesome idea of a point particle, with all its mass or charge concentrated at a location of zero size. Point-like sources often produced infinite quantities in classical theories. If what appeared to be a particle was actually a smooth structure of fields and curved space, perhaps those infinities could be avoided. One arrangement Wheeler and his collaborators studied involved a handle or tunnel in space. Electric field lines could enter one opening and leave through another. An observer who could see only one opening might interpret the outgoing field as evidence of electric charge, even though no charge material had been placed there. The apparent charge would result from the way the field passed through the geometry. This became known as the idea of charge arising without charged matter. The phrase did not mean that conservation laws were being ignored. It meant that what an observer measured as charge might be explained by field lines and global geometry, rather than by a conventional charge particle sitting at the centre. The tunnel would later be described using the word wormhole, another term strongly associated with Wheeler. The image is familiar now, although the modern popular picture often shows a convenient transport gate with excellent lighting and surprisingly reliable destinations. Wheeler's early interest was more cautious. He was investigating what general relativity allowed and whether unusual connections in space could help explain physical properties. These studies prepared the ground for quantum foam because they made the topology of space part of physics. Topology concerns basic patterns of connection. A sphere and a cube have different shapes, but topologically they belong to the same general type, because one can be smoothly reshaped into the other without tearing or attaching new parts. A donut is different because it contains a hole. To turn a sphere into a donut, the pattern of connection has to change. In ordinary general relativity, physicists often choose a spacetime with a particular topology and then calculate how its geometry evolves. Wheeler wanted to know whether quantum theory might allow different topologies to participate in a physical process. Space might not simply bend while keeping the same pattern of connections. At a sufficiently small scale, handles, tunnels, and other features might appear as quantum possibilities. This was a much more radical suggestion than ordinary curvature. A rubber sheet can be bent without being cut. A topological change is more like creating a new passage through the sheet, or separating one region into two. In classical geometry, such changes can create serious mathematical difficulties. In a quantum description, Wheeler suspected that they might become part of the uncertainty of spacetime itself. By the middle of the 1950s, quantum field theory had already shown that the vacuum could not be treated as completely inactive. Fields possessed quantum fluctuations. Processes that were forbidden as permanent classical events could still contribute as temporary intermediate possibilities in quantum calculations. Wheeler asked what would happen if similar reasoning were applied to gravity. Gravity was geometry, so quantum gravitational fluctuations would be fluctuations of geometry. If the fluctuations were weak, spacetime would remain close to one smooth classical shape. At the Planck scale, however, Wheeler argued that they could become large. The change would no longer resemble a small ripple passing over an otherwise dependable surface. The identity of the surface itself could become uncertain. In his work on quantum geometrodynamics, Wheeler examined what might be expected before a complete theory had been constructed. He was clear that the detailed quantization of the gravitational and electromagnetic geometry had not yet been achieved. He was exploring consequences and asking whether the program could help explain elementary particles. His reasoning led him to expect qualitatively new behavior near the Planck length. Gravitational fluctuations could become strong enough to create and destroy complicated structures throughout space. The geometry might briefly contain connections and configurations that did not exist in the large-scale classical description. The word foam captured this expected loss of smoothness. Viewed at ordinary scales, space-time would look calm and continuous. Viewed near the Planck scale, its geometry and topology could appear irregular and rapidly changing. The analogy was not meant to identify a substance. It was meant to compare two levels of description. A distant ocean appears smooth. From closer range, waves become visible. At the surface, bubbles, spray, and small irregular motions replace the simple distant view. Nothing magical happened to the ocean as the observer moved closer. Details that had averaged together became distinguishable. Wheeler proposed that spacetime might have the same relationship between large and small scales. General relativity described the large view. Quantum geometrodynamics would reveal the small view. The smooth geometry would remain accurate for planets, stars, and ordinary laboratory measurements, just as a calm blue patch remains a useful description of the distant sea. It would not reveal every detail underneath. This analogy became so successful that it sometimes creates a false impression of certainty. It encourages us to picture actual little bubbles with definite edges. Wheeler did not possess a complete microscopic theory that calculated a universal population of space-time bubbles. The foam was a physical intuition about large fluctuations of geometry and topology near the Planck scale. The distinction matters because different later theories developed the intuition in different ways. Some researchers studied sums over many possible spacetime geometries. Others considered wormholes connecting distant regions or linking a region to itself. Some investigated whether tiny black holes could appear as temporary quantum processes. Still others concluded that the basic picture of violent topological fluctuation might not survive in a final theory. Wheeler's idea was therefore both specific and open-ended. It was specific in saying that smooth classical geometry should not be trusted at the Planck scale. It was open-ended because it did not settle what the correct quantum structures were, how they evolved, or how they could be observed. The historical setting helps explain why Wheeler was willing to think this way. The middle of the 20th century had already forced physicists to abandon several comfortable assumptions. Quantum mechanics had removed exact classical trajectories from microscopic physics. Relativity had removed universal time and rigid space. Nuclear physics had shown that matter contained stores of energy far beyond ordinary experience. Wheeler had worked closely with leading figures in these developments. He had collaborated with Niels Bohr on nuclear fission. He had studied the quantum behavior of particles and fields. He had contributed to the understanding of gravitational collapse. His research did not divide neatly into quantum theory on one side and gravity on the other. He repeatedly moved between them. He was also unusually skilled at naming ideas. A good name does not prove a theory, but it can make a difficult problem easier to discuss. Terms associated with Wheeler include black hole, wormhole, geon, and quantum foam. Some of these concepts existed in mathematical or physical form before the names became common. Wheeler's language gave researchers and the public a compact way to hold them in mind. The phrase black hole is a useful example. Before that name became standard, physicists used longer and less memorable descriptions for a completely collapsed gravitational object. Black hole conveyed the essential observational feature without requiring a lecture each time. Quantum foam worked similarly. It expressed the idea that the smallest geometry might be fluctuating and irregular, while leaving room for the technical details to develop. There was a risk in this gift for language. A vivid term can travel farther than the qualifications attached to it. Once quantum foam entered popular science, it was sometimes described as though it were a photographed layer of microscopic reality. Tiny wormholes were presented as ordinary objects that definitely appeared and vanished. The uncertainty in the theory was replaced by confidence in the illustration. Wheeler's own approach was more exploratory. He often used bold physical pictures to guide the search for mathematics. The picture was a tool for asking questions. Could geometry generate particle-like properties? Could topology fluctuate? Could a quantum state include different spatial connections? Could the smooth spacetime of general relativity emerge from a deeper and less orderly structure? These were not questions that general relativity alone could answer. Einstein's equations describe how classical geometry responds to matter and energy. They do not provide a full quantum rule for superpositions of geometry. Quantum field theory, meanwhile, normally assumes a spacetime background on which fields operate. It does not automatically explain what happens when the background becomes quantum. Wheeler's quantum geometrodynamics attempted to place the geometry itself at the centre of the quantum description. Instead of beginning with particles moving through a fixed space, it began with possible geometries. The task was to describe how a quantum state could assign amplitudes to different shapes of space and how those possibilities might change. This program eventually led Wheeler and his collaborator Bryce DeWitt toward an important equation for quantum gravity. The equation attempted to describe the quantum state of the geometry of the universe. It also produced a serious puzzle because ordinary time did not appear in the expected way. That problem would influence later debates about whether time is fundamental or emerges from relationships within the universe. The quantum foam idea came earlier and was less mathematically complete, but it already contained the same central change in viewpoint. Space-time was not guaranteed to remain a classical container. It was a physical participant with quantum possibilities. To appreciate how unusual this was, imagine a theatre performance in which the stage floor can exist in several shapes at once. One possible stage is flat, another slopes toward the audience, a third contains a passage connecting opposite sides. The actors and their movements are linked to the possible stages, so there is no single background on which all versions of the performance occur. The analogy still assumes an outer theatre holding the possible stages, which a theory of the whole universe cannot rely on. There may be no external room, clock or observer. The geometry is not changing relative to something outside space-time. The quantum description must be stated using relationships contained within the system. This issue made quantum geometrodynamics conceptually difficult from the beginning. In ordinary quantum mechanics, time is provided as a parameter. A state changes as time passes. General relativity treats time as part of the dynamical geometry. When geometry becomes quantum, the clock used to describe its change cannot simply remain untouched outside the theory. Wheeler's foamy picture did not solve that problem. It made the need for a solution difficult to ignore. If spacetime topology and geometry fluctuate, then the meaning of before, after, near and far may also fluctuate. A tiny tunnel might alter which points count as neighbours. A change in curvature might alter the duration measured along a path. The uncertainty concerns the structure that measurements normally depend on. At the Planck scale, Wheeler imagined these effects becoming substantial rather than remaining small corrections. A smooth geometry would not be one fixed object with a little noise added. It would be an approximation obtained after many microscopic possibilities had been averaged or ignored. The word microscopic is awkward here because it normally refers to small things located in space. Quantum foam would be a proposed microscopic structure of space itself. There is no guarantee that its elements could be assigned ordinary positions. A tiny handle in geometry cannot always be treated like a marble resting at a coordinate. The coordinates are part of the geometry being questioned. Wheeler hoped that this restless structure might do more than modify gravity. It might help explain why particles existed and why they possessed their observed properties. Perhaps the apparent complexity of matter was produced by the complexity of quantum geometry. That larger ambition was not fulfilled. The known elementary particles are successfully described by quantum field theories, with properties that have not been derived solely from Wheeler's original geometrodynamic program. Spin, charge patterns, particle families, and the strengths of interactions require structures that the early proposal did not explain. This does not make the work a failure. Scientific ideas can be valuable even when their first goal is not achieved. Geons helped clarify how fields and gravity could form self-consistent structures. The study of wormholes expanded the understanding of possible geometries. Quantum geometrodynamics helped define the problem of quantizing gravity. Spacetime foam gave researchers a lasting way to discuss the possibility that classical geometry fails at the Planck scale. The idea also changed what counted as a reasonable question. Before this line of thought, one might ask how particles move through space-time. After it, one could ask whether space-time has quantum states, whether topology can be uncertain, and whether geometry itself emerges from something deeper. Later researchers made these questions more precise. Some use path integrals, in which many possible geometries contribute to a quantum process. Some studied simplified universes where topology change could be calculated more easily. Some examined whether wormholes might alter the values of physical constants. Some searched for observable noise or loss of coherence that a foamy space-time might produce. These later developments did not all agree with one another. Even the severity of the foam remained disputed. A straightforward reading of Wheeler's picture suggests that Planck scale geometry is highly irregular. Some modern approaches instead produce quantum structure that is constrained, organized, or effectively smooth. The deepest scale may be unfamiliar without behaving like a storm. That possibility is worth remembering because the word foam encourages disorder. Quantum systems are not simply chaotic. They follow exact rules about possible states and measurement outcomes. A quantum geometry could lack one definite classical shape, while still possessing a highly ordered mathematical structure. Wheeler's contribution was not the claim that he knew the final arrangement. It was the recognition that the arrangement could not be assumed to remain classical. Gravity tied geometry to energy. Quantum theory denied perfect definiteness. At the Planck scale, those lessons met, and the result demanded a new picture. From a comfortable distance, the universe still offered straight rulers, stable clocks, and continuous paths. Move far enough inward, at least in Wheeler's reasoning, and those familiar tools lost their authority. Geometry could fluctuate. Connections could change. Structures might form and disappear before they could become lasting features of the classical world. The next question follows naturally. Once we permit that kind of change, what exactly might appear in the foam? Wheeler's early work pointed toward temporary handles, unusual field configurations, and strong concentrations of gravitational energy. Later descriptions would speak of tiny wormholes, virtual black holes, and geometries that exist only as quantum possibilities. Those phrases require careful treatment. They do not all refer to the same process, and none should be mistaken for an ordinary object repeatedly popping into empty space. To understand what they mean, we have to look more closely at the possible structures hidden inside Wheeler's memorable image. Those hidden structures are often described with three especially memorable phrases: tiny wormholes, virtual black holes, and fleeting geometry. Each phrase gives us a useful picture, but each can also suggest more certainty than the physics allows. None of them refers to an object that has been directly observed. They are possibilities that appear when physicists try to apply quantum reasoning to spacetime at the Planck scale. Start with the wormhole. In its simplest popular form, a wormhole is imagined as a shortcut between two distant places. A traveller enters one opening, crosses a tunnel, and emerges somewhere else without moving through all the space in between. This is a convenient picture for science fiction, where the tunnel is usually wide, stable, and located close enough to the main characters to save considerable fuel. The mathematical idea is less comfortable. A wormhole is not necessarily a tube lying inside ordinary space. It is a feature of the way space or space-time is connected. Two regions that appear far apart in the large-scale geometry may share an additional connection. The connection is part of the geometry itself. There is no need for the tunnel to curve through a larger external room. A map can offer a limited comparison. Imagine two towns printed on opposite ends of a sheet of paper. According to the roads on the sheet, they are far apart. Now imagine adding a new road that directly joins them. The distance defined by the road network changes, even though the towns have not moved across the page. A wormhole changes the available connections in a much deeper geometric way. The comparison should not be pushed too far. A paper map sits on a desk and can be folded through a surrounding space. Space-time does not need to bend into an outside dimension to contain a wormhole. The shortcut can be described through its internal geometry. Folding paper is only a visual aid, not a statement about what space-time is physically doing. The historical ancestor of the modern wormhole was the Einstein-Rosen bridge. Albert Einstein and Nathan Rosen studied a solution in which two sheets of space were connected by a bridge. Their goal was not to design a transport system. They were exploring whether particles could be represented by regular geometric structures rather than by singular points. The bridge later became part of the history of wormhole physics, but the original solution was not a stable passage that a person could cross. Wheeler extended the discussion by asking whether small handles and unusual connections could appear in quantum geometry. If the topology of space becomes uncertain, then a region might briefly have one pattern of connection in one quantum possibility and a different pattern in another. What looks smooth and simply connected at a large scale might include temporary microscopic handles at the Planck scale. A handle is a topological feature rather than a material object. Imagine the difference between the surface of a ball and the surface of a ring-shaped object. The ring has a route through its central opening that the ball does not possess. Changing one into the other requires a change in topology. Wheeler suspected that quantum gravity might permit such changes at very small scales, even though the classical geometry around us keeps one stable form. This is the origin of the tiny wormhole picture. At the Planck scale, space-time might not merely curve by a slightly different amount, its connections might fluctuate. A microscopic passage could appear as part of an intermediate quantum geometry and then disappear again. From far away, the brief feature would be averaged into the ordinary smooth space-time we observe. The word appear is risky here. It may sound as though a finished tunnel suddenly materializes at a definite place, remains open for a definite interval, and then shuts. A genuine quantum description may not assign it such a clear history. The wormhole could be one contribution among many possible geometries. Asking exactly when it existed might be no more appropriate than asking which path a quantum particle definitely followed when the experiment does not select one path. Quantum theory often describes a process by considering several possible intermediate histories. These histories contribute to the probability of the final outcome. They are not always events that can be isolated and observed while they are supposedly taking place. The same caution applies to a foamy geometry. A tiny wormhole may be part of a calculation without behaving like a classical object hidden behind the laboratory wall. The distinction becomes even more important with virtual black holes. The adjective virtual does not simply mean very small, short-lived, or difficult to photograph. In quantum theory, virtual objects are usually internal elements of a calculation. They connect the initial and final states of a process. They do not have to obey the same conditions as particles that can travel freely into a detector. Popular explanations often say that virtual particles borrow energy, exist briefly, and repay it before nature notices. This is memorable, but it is not a reliable account of the theory. Quantum mechanics does not operate a lending office, and energy conservation does not take short breaks. Virtual particles are features of a perturbative method used to calculate interactions. They should not automatically be treated as ordinary particles that secretly exist between measurements. A virtual black hole carries the same warning. It is not necessarily a miniature version of an astronomical black hole, complete with a lasting horizon and a tiny central singularity. Near the Planck scale, the classical ideas used to define a black hole may become uncertain. The geometry may not remain stable long enough for an ordinary event horizon to have one exact shape. The term is used for quantum gravitational configurations that resemble black hole formation in an intermediate process. Energy becomes concentrated. Geometry responds strongly. A trapped or nearly trapped region may be involved. The configuration contributes to a quantum process and then does not remain as a lasting object in the final state. Stephen Hawking developed one influential version of this idea in work on spacetime foam. He considered particular topological fluctuations in a Euclidean approach to quantum gravity and interpreted some of them as closed loops of virtual black holes. In this picture, Planck-scale black hole configurations were not isolated permanent objects. They were part of the fluctuating topology included in the gravitational quantum process. The word Euclidean needs a quiet explanation because it changes the character of time in the calculation. Ordinary space-time distinguishes time from space. That distinction produces light cones, causal order, and the familiar difference between moving through a room and waiting for an hour. In some quantum gravity methods, physicists transform the time coordinate so that the mathematics resembles the geometry of four spatial directions. This does not mean the real universe literally has four ordinary spatial directions and no time. The transformation is a mathematical technique. It can make certain calculations more manageable and reveal important solutions called instantons. After the calculation, researchers try to connect the result back to physical space-time with an ordinary time direction. Euclidean quantum gravity has produced valuable insights, especially in black hole thermodynamics and early universe cosmology. It also contains unresolved problems. The sum over possible geometries is difficult to define. The relation between Euclidean configurations and real-time physics can be subtle. A bubble that appears clearly in the transform calculation should not be announced as a confirmed object moving through physical space-time. This is one reason descriptions of virtual black holes vary. In one context, the phrase refers to a specific Euclidean topological contribution. In another, it is a rough name for any Planck-scale fluctuation strong enough to resemble a black hole. In still another, it appears in effective arguments about how quantum gravity might modify particle interactions. These uses are related, but they are not identical. A full theory would need to tell us what counts as a black hole when the geometry is in a quantum state. In classical relativity, a black hole is defined globally. Whether an event lies inside the black hole depends on whether a signal from that event can ever reach the distant future. This definition assumes a definite space-time extending through time. A fluctuating quantum geometry may not provide one definite causal structure. One possible geometry may contain a trapped region while another does not. The future needed for the classical definition may itself be part of the uncertainty. Researchers can use more local ideas such as temporary trapped surfaces, but the familiar phrase black hole may be doing more work than the underlying theory has earned. The scale also changes what we should expect from evaporation. A large black hole has a horizon that can be treated using quantum fields on an approximately classical geometry, and those fields produce Hawking radiation. As the black hole loses mass, it shrinks and becomes hotter. Near the Planck scale, that approximation breaks down. Gravity is strongly quantum, and the final state cannot be predicted confidently using the calculation alone. A virtual black hole in spacetime foam is not simply the last moment of an evaporating stellar black hole played repeatedly in empty space. It belongs to a proposal about the quantum vacuum of gravity. The similarity is that both lead toward Planck scale geometry. The difference is that one begins with a large collapsed object, while the other is an intermediate fluctuation in a proposed microscopic description. Tiny wormholes and virtual black holes are often discussed together, because black hole geometries can contain bridge-like structures. The two mouths of a wormhole can resemble gravitational objects when viewed from outside. A pair of black holes can be connected in certain idealized solutions. In a quantum process, the creation and disappearance of such configurations can be represented by geometries with unusual topology. This does not mean every virtual black hole is a usable wormhole, or that every wormhole has black hole horizons. The categories overlap in some models and separate in others. A wormhole concerns connection. A black hole concerns causal trapping. One geometry can possess both properties, but neither word automatically guarantees the other. Travel through these Planck scale structures is not part of Wheeler's basic foam picture. Even a macroscopic wormhole permitted by a mathematical solution may pinch off too quickly to cross. Keeping a traversable wormhole open generally requires unusual forms of stress and energy. No natural macroscopic traversable wormhole has been observed. A microscopic quantum wormhole would present an even greater problem. Its characteristic size could be near the Planck length. It might not have a definite classical interior. It might contribute only as an intermediate geometry. Describing a person entering it would be like planning to sail through one molecule in a glass of water, except that the molecule has not been shown to exist, and the idea of sailing through it may not apply. The time machine stories can also be set aside. Some wormhole arrangements in classical relativity can be manipulated into geometries containing closed paths through time. Such proposals raise severe issues involving causality, stability, and quantum fields. Classical topology change is already constrained by results showing that changing spatial connections often comes with singular behavior, causal violations, or failures of ordinary assumptions. Quantum gravity may alter those conclusions, but has not supplied an experimentally supported method for visiting yesterday. The main interest of microscopic wormholes is not transportation. It is what they might reveal about the quantum state of geometry. If different topologies contribute to physical processes, then the vacuum of gravity is more complicated than one gently fluctuating shape. The set of possible connections becomes part of the quantum description. This brings us to fleeting geometry. The phrase is broader than wormholes or black holes. A geometry can fluctuate without forming either one. Distances can vary. Curvature can change. Light cones can tilt. Areas and volumes can become uncertain. The relation between nearby events can differ across possible quantum states. Imagine measuring the distance between two markers many times. In an ordinary quantum experiment, the markers themselves may move slightly because their positions are uncertain. In a quantum geometry, there could be an additional uncertainty in the distance relation itself. Even after accounting for the matter used as markers, the space-time state may not assign one exact classical separation. This does not imply that a ruler would visibly flicker. At large scales, the quantum alternatives must combine into the stable geometry tested by experiments. The fluctuations would become important only when measurements approach the relevant energy and distance scale. The larger world is protected by averaging, suppression, decoherence, or some combination of these mechanisms. Fleeting geometry also does not require time to be divided into tiny snapshots. The geometry need not hold one shape, switch to another, and switch back according to a universal hidden clock. In quantum gravity, time is part of the system. The word fleeting is an ordinary language approximation for a structure that contributes over a limited range of a physical process. A more careful statement would describe correlations between measurable events. A pulse of light travels from one physical clock to another, the elapsed time varies slightly across repeated preparations. A pattern of matter becomes entangled with possible gravitational fields. A quantum process receives contributions from geometries with different curvature or topology. These are operational statements tied to possible measurements. The foam picture compresses all of that into an image of tiny features forming and disappearing. It is useful because the full mathematical language is difficult. It is dangerous because the image encourages us to replace uncertain quantum histories with a miniature classical movie. There is also no agreement that topology must fluctuate freely. Classical relativity makes topology change difficult. Quantum approaches may include different topologies, but defining their contributions is technically and conceptually challenging. Some approaches to quantum gravity keep topology fixed and quantize geometry within it. Others allow topology change only under controlled conditions. Some replace smooth geometry with discrete structures where the question must be reformulated. String theory contains processes in which the geometry of additional dimensions can change topology, while the complete physical description remains well behaved. Other string-based models include microscopic handles and extended objects. Loop-based approaches focus on quantum states of areas, volumes, and connections rather than beginning with a sea of tiny wormholes. Causal approaches often restrict the allowed histories to preserve a sensible order of events. These differences tell us that Wheeler's foam is a research question, not a universal ingredient that every theory reproduces in the same way. The underlying Planck scale state might be topologically busy. It might be highly constrained. It might have no smooth topology until a large-scale limit emerges. Suppose tiny wormholes did contribute to low-energy physics. They might alter how fields propagate or interact. A field could enter one microscopic connection and emerge in a way that looks, at larger scales, like a small correction to an ordinary interaction. A large population of such contributions could affect effective constants, vacuum energy, or the preservation of quantum information. These possibilities have motivated extensive theoretical work, but they have not produced one accepted observational signature. Some older proposals suggested that wormholes could influence the values of physical constants, or help explain the cosmological constant. The conclusions depended strongly on assumptions about the gravitational quantum description and the treatment of many wormholes. Later work exposed serious ambiguities and instabilities. Virtual black holes have also been proposed as sources of processes that are extraordinarily rare in ordinary particle physics. If a Planck scale configuration does not preserve some of the symmetries respected by lower energy interactions, it might permit small violations of quantities that otherwise appear conserved. Estimates of effects such as particle decay then depend on the unknown rules of quantum gravity. No confirmed observation requires virtual black holes as an explanation. The phrase remains part of theoretical exploration. It is a way to ask what strong quantum fluctuations of gravity might do, not a detected population waiting to be counted. One issue concerns quantum coherence. A particle interacting with an inaccessible microscopic geometry could appear to lose information when only the visible part of the system is measured. Hawking's virtual black hole model proposed a form of coherence loss through topological fluctuations. That conclusion was tied to the framework he used, and is not a general result accepted across all approaches to quantum gravity. Modern work on black hole information has made many physicists cautious about fundamental information loss. Developments in holography and quantum gravity suggest that apparently missing information may be encoded in subtle correlations rather than destroyed. This does not directly settle the behaviour of Wheeler's foam, but it shows why older claims cannot simply be carried into every modern theory. Microscopic wormholes have also acquired a new role in discussions of entanglement. Some theories suggest a relationship between quantum entanglement and geometric connections. In holographic models, the structure of entanglement can help determine the shape of an emergent spacetime. A wormhole may then represent a pattern of quantum correlation rather than a tunnel drilled through a pre-existing space. This idea should not be confused with evidence that every entangled pair is joined by a traversable passage. The proposed connection is mathematical and theory dependent. It becomes clearest in special models of quantum gravity. It does not allow messages to be sent faster than light, and it has not turned laboratory entanglement into a transport network. Experiments performed on quantum processors have simulated systems whose mathematical descriptions are related to traversable wormhole models. These experiments studied the movement of quantum information in a controlled many-body system. They did not create a gravitational wormhole in physical space. The distinction is similar to using water waves to simulate features of another physical system. The simulation can teach us about the mathematics without producing the object represented by the mathematics. The lack of direct observation leaves us with several levels of confidence. Strong quantum effects should matter when gravity reaches the Planck regime. That is a widely shared expectation. The classical geometry should then be replaced or extended by a quantum description. That is also broadly expected. Large fluctuations of topology, microscopic wormholes, and virtual black holes are more specific proposals. They are plausible in some frameworks and absent or transformed in others. The correct picture may contain parts of Wheeler's intuition, without resembling foam in a literal visual sense. A future theory might describe transitions among quantum networks. It might explain smooth geometry through entanglement. It might include extended objects whose interactions change the effective topology. From the perspective of ordinary space-time, any of these could look like fleeting geometry. And what matters is not whether the deepest layer resembles soap bubbles. The important claim is that geometry may participate in quantum processes. The distance between events, the curvature around energy, and the pattern of connections may not remain fixed while matter behaves quantum mechanically inside them. Once that step is taken, the separation between quantum physics and gravity becomes impossible to maintain. Quantum theory needs a setting in which states and interactions can be described. General relativity says that the setting is affected by the states and interactions. Near the Planck scale, each theory changes the conditions required by the other. Tiny wormholes and virtual black holes are attempts to picture the resulting tension. They show what may happen when geometry is allowed to explore quantum alternatives. Some alternatives contain new connections, some contain temporarily trapped regions. Most leave no lasting classical structure. Together, they form the more detailed content hidden inside the broad phrase quantum foam. But a collection of suggestive structures is not yet a theory. We still need rules that say which geometries are allowed, how much each possibility contributes, how causal order survives, how ordinary space-time emerges, and what an experiment should measure. Answering those questions requires the larger task that Wheeler's work helped define, bringing quantum mechanics and gravity into one consistent description. Bringing quantum mechanics and gravity together sounds at first like a straightforward task. Physics already contains several forces, and quantum theory describes most of them extremely well. Gravity should simply be added to the same framework, given its own quantum particle, and placed beside the other interactions. That was the reasonable expectation. It was also where the trouble began. Quantum mechanics and general relativity are both successful theories. Neither one survives by reputation alone. Quantum mechanics predicts the behavior of atoms, particles, light, and materials with extraordinary accuracy. It lies behind lasers, computer chips, medical scanners, and much of modern chemistry. General relativity predicts the motion of planets, the bending of light, the slowing of clocks in gravity, the behavior of black holes, and the passage of gravitational waves. When either theory is used in the situations it was designed to describe, it works remarkably well. The difficulty appears when a physical system requires both at once. An atom needs quantum mechanics, but its gravitational field is so weak that ordinary gravity can usually be ignored. A planet needs general relativity when high precision is required, but its quantum uncertainty is far too small to matter in normal calculations. Nature kindly keeps the two theories in separate offices for most everyday work. Black holes, the early universe, and the Planck scale do not respect that arrangement. They combine concentrated energy, strong gravity, and quantum effects in the same place. A description that ignores either side becomes incomplete. The disagreement begins with the role of spacetime. In ordinary quantum theory, particles and fields are described as changing within space and time. A laboratory clock supplies the time. A coordinate system tells us where measurements occur. The quantum state can be uncertain, but the background used to describe that uncertainty is usually treated as fixed. General relativity removes that fixed background. Space-time is not a rigid container. Its geometry changes in response to matter and energy. The clocks, distances, and paths used in an experiment depend on the gravitational field. The background is part of the physical system. Trying to combine the theories therefore creates an unusual question. How do we describe quantum uncertainty when the structure used to define location and time is also uncertain? Suppose a particle can follow two possible paths. Quantum mechanics allows those alternatives to contribute to the final result. If the particle carries energy, each possible path produces a slightly different gravitational field. The two paths are then connected with two possible geometries. In an ordinary approximation, the difference is too small to notice. We calculate the particle as a quantum object and treat space-time as one fixed background. Near the Planck scale, that shortcut may fail. The geometry cannot be chosen first and left untouched. Matter and space-time have to enter the quantum description together. One possible state might contain energy concentrated in one region. Another might place it elsewhere. General relativity says those arrangements curve space-time differently. A full quantum state would then include alternatives involving both matter and geometry. This is more complicated than an object occupying two positions on one stage. The stage itself changes with the object. One version of the stage may be curved one way, while another version is curved differently. There is no single classical surface shared by every possibility. Time causes an even deeper problem. In standard quantum mechanics, time is the parameter used to describe change. A quantum state at one time is related to the state at a later time. The clock remains outside the system being calculated. General relativity treats clocks as physical objects. Their rates depend on motion and gravity. There is no single universal time shared by every observer. The theory describes relationships between events rather than evolution according to one external cosmic clock. Once the gravitational field becomes quantum, the clock can no longer remain safely outside the calculation. It must be made from physical matter, and that matter interacts with the quantum geometry. The device used to label change becomes part of the changing system. This is known as the problem of time in quantum gravity. The name sounds as though the universe has misplaced its schedule, which is not entirely unfair. The problem is not that nothing happens, it is that the familiar method of describing what happens relies on a time variable that general relativity does not treat as an independent background. John Wheeler and Bryce DeWitt encountered this issue while developing a quantum description of geometry. Their approach assigned a quantum state to possible shapes of space and the matter within them. The resulting framework did not contain time in the ordinary form expected from quantum mechanics. Instead of describing a universe moving through an external time, the equation placed relationships among possible geometries and matter configurations at the centre. The complete state appeared static. There was no obvious clock standing beyond the universe and moving the entire calculation forward. That result did not prove that change is an illusion. It showed that time might have to be recovered from relationships inside the universe. One physical system can serve as a clock for another. A changing field, an expanding region, or a sequence of correlated records can provide an internal measure of time. Imagine a room with no wall clock and no view outside. Two people can still compare events by using regular changes within the room. One may count the swings of a pendulum while the other records the cooling of a cup of tea. Neither process provides an external universal time, but each can be used to describe the other. Quantum gravity may require a more precise version of this relational idea. Time would not be a separate substance flowing behind events. It would be a way of comparing physical changes. The challenge is to recover the stable time used in laboratories from a deeper theory in which clocks and geometry are both quantum systems. Another problem appears when physicists try to calculate quantum corrections to gravity using the methods that work for other forces. In quantum field theory, interactions are often calculated as a sequence of increasingly complicated contributions. Each contribution represents possible intermediate processes. These calculations can produce infinite quantities. For the electromagnetic, weak, and strong interactions, physicists developed a procedure that reorganizes the infinities into a finite set of measurable properties. Once those properties are fixed by experiment, the theory can make precise predictions at other energies. Applying the same method directly to general relativity does not work in the same complete way. At higher stages of the calculation, new kinds of infinite terms appear. Each one would require another measured quantity to control it. The list does not close after a finite number of adjustments. This is often described by saying that general relativity is not renormalizable when treated as an ordinary fundamental quantum field theory. The phrase can sound like a declaration that quantum gravity is impossible. It is not. The failure tells us that the straightforward method cannot define the complete theory at arbitrarily high energies. It does not stop gravity from being treated quantum mechanically at low energies. Physicists use general relativity as an effective field theory. This means they accept that it is a large-scale approximation, while calculating small quantum corrections within the range where the approximation remains reliable. The unknown Planck scale physics is represented by additional effects that become increasingly weak at lower energies. The method is similar to describing waves in water without tracking every molecule. The theory works because the omitted microscopic details have little influence on long waves. At shorter distances, more information about the underlying structure becomes necessary. Quantum gravity as an effective theory can make meaningful low-energy predictions. It shows that there is no immediate contradiction in discussing quantum gravitational effects. The serious failure appears only when the calculation is pushed toward the Planck scale, where the deeper theory is needed. Within this low-energy picture, the gravitational field can be described in terms of quantum excitations called gravitons. A graviton would play a role related to the role played by a photon in the electromagnetic field. It would be massless and would carry changes in the gravitational field. No individual graviton has been detected. Gravity interacts so weakly with ordinary matter that detecting one would require an instrument of unreasonable sensitivity. A graviton could pass through a vast amount of material without leaving a clear signal. Building a detector for one has been compared with trying to notice a single snowflake landing during an earthquake, except the snowflake also ignores most of the detector. The absence of direct detection does not make the graviton an arbitrary invention. When small gravitational disturbances are quantized on an approximately smooth spacetime, the graviton appears naturally. String theory also contains a vibration with the properties required of a graviton. The concept is strongly motivated, even though direct observation remains far beyond current experiments. The graviton description is useful when spacetime is close to a fixed classical geometry. Near the Planck scale, the disturbance may no longer be small. There may be no stable background on which the graviton travels. A theory built only from tiny ripples cannot describe a situation in which the entire ocean is uncertain. Several research programs attempt to provide that deeper description. They begin from different assumptions, use different mathematical tools, and often give different pictures of what spacetime becomes. String theory replaces elementary point particles with tiny extended strings. Different patterns of string vibration appear as different particles. One vibration behaves like a graviton, which means gravity is included without being added as a separate afterthought. The extended nature of strings changes interactions at very short distances. Point particles meet at exact locations, where calculations can become badly behaved. Strings spread an interaction over a small region. This softens some of the high-energy problems that appear when gravity is quantized directly. String theory normally requires additional spatial dimensions beyond the three large ones we experience. Those dimensions may be compact and too small to observe directly. The theory also includes higher dimensional objects, commonly called branes, and a large network of mathematical relationships connecting descriptions that once appeared unrelated. In this framework, the smallest structure is not necessarily Wheeler's violent sea of random wormholes. Geometry can change, strings can split and join, and topological transitions can occur. Yet the full string description may remain controlled even when the classical geometry looks singular or changes its connection. String theory has also produced one of the strongest clues that spacetime might emerge from quantum information. In certain models, a gravitational theory inside a region can be equivalent to a quantum theory, defined without gravity on its boundary. The geometry of the interior is connected with patterns of entanglement in the boundary theory. This idea is known as holography. It does not mean the visible universe is a projected image on a nearby wall. It means that, in specific theoretical settings, the information needed to describe a gravitational region can be represented by a theory with fewer spatial dimensions. Holography has provided detailed tools for studying black holes and quantum gravity. It has shown how a smooth spacetime can be related to quantum relationships in a theory where that spacetime is not fundamental. It has also strengthened the belief that black hole evaporation can preserve information. The best understood examples involve universes with properties different from the observed cosmos. Extending the results to our own universe remains difficult. String theory has not yet produced one experimentally confirmed description of the particles, dimensions, and cosmic conditions we observe. Loop quantum gravity takes another route. It begins with general relativity and attempts to quantize geometry without first introducing a fixed background. Instead of placing quantum fields on spacetime, it describes quantum states of spacetime itself. The basic states can be represented by networks. Links and meeting points in those networks carry information related to areas and volumes. Geometry does not appear as one smooth surface at the smallest level. It is built from quantum relationships. Areas and volumes can have discrete possible values in this approach. That does not turn space into a regular grid of cubes. The network is not placed inside an existing room. Its connections help define the geometry that a room would have at a larger scale. As these networks change, they can form structures called spin foams. The use of foam here is related to quantum histories of geometry, but it should not be confused automatically with Wheeler's image of tiny wormholes. A spin foam is a mathematical structure describing transitions among quantum geometric states. It does not necessarily contain bubbles, tunnels, or virtual black holes. Loop quantum gravity has produced important results concerning discrete geometry and black hole entropy. Related models suggest that classical singularities may be replaced by quantum behavior. In some cosmological calculations, a collapsing universe reaches a very dense state and then begins expanding rather than ending at an infinite singularity. These results are promising, but they depend on models and approximations. Recovering ordinary smooth spacetime and the full behavior of matter at large scales remains a major task. The theory must explain not only small geometric units, but also why they combine into the general relativity observed around stars and galaxies. Other approaches explore different possibilities. Causal dynamical triangulations build space-time histories from simple, geometric pieces, while preserving a distinction between cause and effect. Large collections of the pieces can produce an extended universe with familiar dimensions, even though the small-scale structure behaves differently. Causal set theory begins with discrete events, and the order in which they can influence one another. Distance and geometry are expected to emerge from that causal structure. The starting point is not a smooth space, but a network of before and after relationships. Asymptotic safety investigates whether gravity can remain mathematically controlled at extremely high energies, because its interactions approach a special fixed pattern. In that case, gravity might not require strings or a discrete network to become consistent. The same basic field theory could possess a well-defined high-energy completion, although its behavior would differ greatly from the low-energy version. Group field theories, tensor models, non-commutative geometry, emergent gravity, and other programs add more possibilities. The long list does not mean physicists are selecting theories at random. Each approach responds to genuine problems. Each preserves some principles while changing others. The disagreement concerns which principles are fundamental and which ones emerge only at larger scales. Black holes provide a testing ground for these ideas because they force quantum theory, gravity, and thermodynamics into the same discussion. A black hole has entropy, meaning it can be assigned a number of possible microscopic states. Its entropy is related to the area of its horizon rather than the volume inside. That area relationship is unusual. In ordinary systems, the amount of information generally grows with volume. Black holes suggest that the maximum information contained in a region may instead be linked to its boundary. A successful theory of quantum gravity should explain what the microscopic black hole states are. String theory has counted them in certain special black holes and obtained the expected entropy. Loop quantum gravity has also derived the area relationship by counting quantum geometric states under particular assumptions. These successes do not show that the theories are equivalent or that either one is complete. They show that black hole thermodynamics contains important clues. Any theory that ignores those clues is unlikely to describe quantum spacetime correctly. The information problem adds another test. Hawking's original calculation suggested that black hole radiation was thermal and carried no detailed record of what formed the black hole. If the black hole vanished completely, information about the initial quantum state seemed to disappear. Ordinary quantum mechanics does not allow fundamental information to be destroyed in that way. A state can become extremely complicated and practically impossible to reconstruct, but its evolution preserves the information in principle. Resolving this conflict has driven decades of work. Holographic methods now provide strong evidence that information is preserved in several well-understood models. The radiation can contain subtle correlations that are invisible in the simplest approximation. What looks like loss may result from treating the geometry too classically and ignoring connections within the full quantum state. This lesson may also change how we think about quantum foam, a collection of independent microscopic black holes that simply absorbs information would be difficult to reconcile with a unitary quantum theory. The deeper geometry may preserve information through correlations that Wheeler's first picture did not include. The same possibility applies to wormholes. In modern calculations, wormhole-like geometries can connect different contributions to a quantum process and help reproduce the expected information behavior. This does not prove that physical space is filled with traversable tunnels. It shows that unusual geometries may encode correlations rather than acting as random holes in reality. No approach has yet passed every required test. A complete theory must recover general relativity at large distances. It must agree with quantum field theory where gravity is weak. It must explain black hole entropy and information. It must describe the early universe without relying on uncontrolled infinities. It should tell us whether spacetime is continuous, discrete, emergent, or something that does not fit those simple categories. Most importantly, it must connect with observation. Mathematical consistency is essential, but nature is not required to choose the theory with the most elegant seminar slides. The lack of a confirmed theory does not mean nothing has been learned. Low-energy quantum gravity is well defined as an effective theory. Black hole thermodynamics places strict demands on microscopic descriptions. Holography demonstrates that space-time can emerge in controlled models. Loop-based approaches show how geometry can possess quantum states without a fixed background. Other programs reveal ways that dimension, causality, and smoothness might arise from simpler structures. These results make the original image of quantum foam more complicated. Wheeler imagined violent fluctuations of geometry and topology near the Planck scale. A modern theory may contain that behaviour, but it may also replace it with something more organised. The smallest scale could resemble a fluctuating network rather than bubbles. It could be made from extended quantum objects. It could consist of causal relations among events. It could have no independent geometry until entanglement builds one. The word foam survives because it reminds us not to extend classical smoothness without limit, but it does not tell us which description is correct. Whatever the answer, the familiar space-time around us must emerge with remarkable accuracy. Clocks must behave according to relativity. Light must travel along predictable paths. Planets must follow the measured geometry. Quantum fields must retain the behaviour tested in laboratories. This requirement hides the Planck scale extremely well. Any large effect would already have disrupted known physics. A successful quantum gravity theory must make its new structure almost invisible under ordinary conditions. Almost invisible is not necessarily completely invisible. Small effects can accumulate. A photon can travel for billions of years before reaching a telescope. A gravitational wave can cross an enormous cosmic distance. An interferometer can compare lengths with precision far beyond everyday measurement. The early universe may have enlarged microscopic fluctuations until they influence structures visible today. These possibilities turn the problem from one of theory into one of detection. If space-time has a quantum texture, the texture may disturb light, add noise to distance measurements, alter the behaviour of particles, or leave a pattern in signals from the distant universe. Most proposed effects are extremely small. Many have already been restricted by observations. Some simple foam models predict disturbances that should have been seen and therefore cannot describe nature. Other models remain safely below present sensitivity. The next step is not to assume that quantum foam must leave a dramatic mark. It is to ask what kind of trace a particular theory predicts, whether another process could imitate it, and whether an instrument can separate the effect from ordinary noise. That search takes us away from the imagined Planck-scale pictures and toward telescopes, particle detectors, atomic clocks, and the most precise measurements humans can make. That search begins with an awkward fact. The Planck scale is far beyond the reach of any microscope, particle accelerator, or direct measuring device that exists today. If quantum foam is confined to distances near the Planck length, we cannot simply enlarge a sample, place it under a lens, and inspect the result. There is no container of space-time foam waiting on a laboratory shelf, which is probably fortunate because the storage instructions would be difficult to write. This does not make the idea untestable. Physics often studies things that cannot be reached directly. Scientists learned about the interiors of stars by examining the light that escaped from them. They inferred the existence of atoms before individual atoms could be imaged. Black holes were studied through their effects on nearby matter, long before gravitational waves from merging black holes were detected. The same basic strategy can be applied to quantum spacetime. Instead of observing the Planck scale itself, researchers look for small effects that might survive at larger scales. A disturbance too small to measure over a meter might accumulate while light crosses billions of light years. A tiny uncertainty in position might appear as unexplained noise in an extremely sensitive interferometer. A small change in the propagation of a high-energy particle might become noticeable after a long journey through the universe. There is an important condition attached to every one of these searches. Quantum foam does not produce one universally agreed prediction. The phrase refers to a family of ideas about the small-scale structure of space-time. Different models predict different effects, and some predict no detectable effect with present technology. Scientists therefore cannot perform a general quantum foam experiment that gives a simple yes or no result. They must choose a particular model, calculate what that model would do to a measurable system, and compare the prediction with observation. When no effect is found, the result constrains that model. It does not automatically prove that space-time is perfectly smooth at every scale. Light is one of the most useful tools in this search because it can travel across enormous distances while carrying information about its journey. A photon emitted in a distant galaxy may cross much of the observable universe before entering a telescope. If spacetime has a small irregularity that affects propagation, the long journey might magnify the result. One proposed effect is a slight dependence of the speed of light on the energy of the photon. In ordinary relativity, light in a vacuum has the same speed regardless of its energy. A low-energy radio photon and a much more energetic gamma-ray photon follow the same basic rule. Some quantum gravity models modify that rule by an extremely small amount. Higher energy photons might travel slightly more slowly or slightly more quickly than lower energy photons. The difference over an ordinary distance would be impossible to notice. Across billions of light years, however, even a tiny difference could create a measurable delay. Gamma-ray bursts provide useful tests because they are extremely bright, distant, and brief. They can release photons across a wide range of energies during a short event. Researchers compare the arrival times of lower and higher energy photons to look for a pattern that increases with energy and distance. The main difficulty is that a delay can begin at the source. A gamma-ray burst is a violent and complicated event. Photons of different energies may be emitted at different moments because of the physical processes producing the burst. If a high-energy photon arrives later, scientists cannot immediately conclude that spacetime slowed it down. The source may simply have sent it later. Researchers deal with this problem by studying the detailed structure of the signal, comparing several statistical methods, using conservative assumptions about possible delays at the source, and examining multiple bursts at different distances. The results have placed strong limits on simple models in which the speed difference grows directly with photon energy at around the Planck scale. No accepted energy-dependent delay caused by quantum gravity has been detected. Some of the best-studied gamma-ray bursts have constrained the relevant scale beyond the Planck energy for certain forms of the proposed effect, while newer work continues to test more complicated possibilities involving cosmic curvature. That result is easy to misunderstand. It does not mean physicists have looked at quantum foam and found it empty. It means that particular models predicting a certain type and size of delay do not fit the observations. A theory that preserves the ordinary speed of light, produces a much weaker effect, or changes propagation in another way would not be ruled out by the same test. Another possible trace involves the phase of light. Light behaves as a wave, and a clear astronomical image depends on different parts of the wavefront maintaining an orderly relationship. Telescopes use that relationship to focus light from a distant point into a sharp image. If space-time introduces random changes in the distance travelled by different parts of the wave, the phases may become disordered. The effect is similar to looking through uneven glass. A point source could become blurred, surrounded by a faint halo, or eventually impossible to distinguish. Again, the Planck length is far too small for one fluctuation to matter. The question is whether the disturbances accumulate. Different models give very different answers. In a random walk model, each small change is added with a partly random direction. Some changes cancel while others build up, rather like taking many steps chosen by repeated coin tosses. In other models, the accumulation is weaker because neighbouring fluctuations are correlated, or because the quantum structure cannot be treated as independent steps. The distinction is crucial. A small change repeated over a cosmic distance can become large in one model and remain negligible in another. Calling both models quantum foam does not make their predictions interchangeable. Astronomers have examined sharp images of distant quasars and other compact sources to search for the expected blurring. Some of these photons have travelled for billions of years. If certain simple accumulation models were correct, their wavefronts should have become distorted enough to damage or erase the images. The fact that distant sources remain visible and sharply localized has ruled out several proposed models, including strong random walk behavior and some versions of holographic accumulation. These observations provide powerful constraints because shorter wavelength radiation is more sensitive to small path differences. X-ray and gamma-ray detections extend the test beyond ordinary visible light. This is an example of a negative result doing useful scientific work. A telescope did not detect a new object or a dramatic flash. It found that an expected loss of image quality was absent. That absence tells us that space-time cannot disturb light in certain proposed ways. Polarization provides another sensitive tool. Light can carry a preferred direction in the orientation of its electromagnetic field. Some proposed modifications of space-time would cause different polarization states to travel differently. Over a long distance, the original polarization could rotate, become distorted, or wash out. Astronomers can measure polarized light from distant sources and compare it with what the source is physically capable of producing. Strong polarization arriving in intact places limits on models that would separate or scramble the different states during the journey. These tests are often discussed as searches for violations of Lorentz symmetry. Lorentz symmetry is the principle behind the agreement of inertial observers about the basic laws of physics and the special status of the speed of light. A crude space-time lattice with one fixed orientation could violate that symmetry by giving the universe a preferred direction or state of motion. Not every discrete or quantum space-time theory violates Lorentz symmetry. Some are built to preserve it exactly. Others predict small departures only at high energies. Observational limits on symmetry violation therefore constrain specific theories rather than the general idea of quantum geometry. High-energy cosmic rays also contribute. These particles reach Earth with energies far beyond those produced in ordinary radioactive processes. If the relationships between energy, motion, and particle mass were modified, reactions that are normally forbidden might become possible. Particles could decay too quickly, lose energy through new processes, or fail to reach Earth in the observed numbers. The survival of high-energy particles across large distances can therefore eliminate proposed modifications. This method does not inspect space-time directly. It tests whether the ordinary rules of particle propagation remain valid under extreme conditions. Gravitational waves offer another messenger. These waves are changes in space-time geometry, produced by accelerating masses, particularly compact objects such as black holes and neutron stars. If quantum structure affects the movement of gravitational waves, it might produce dispersion, scattering, loss of coherence, or a change in speed. The combined observation of gravitational waves and gamma rays from a neutron star merger showed that the two signals travelled at almost the same speed across a vast distance. The emission times were not exactly identical and depend on the astrophysics of the merger, so the comparison requires care. Even with that uncertainty, the result placed very strong limits on theories predicting a substantial difference between the speed of gravity and the speed of light. This does not directly test every version of quantum foam. A foamy space-time could preserve the common speed of light and gravity. The observation is valuable because it removes another large region of possible modifications. Gravitational wave detectors can also search for unusual background noise. Instruments such as laser interferometers compare the lengths of two paths. A laser beam is divided, sent along different directions, reflected and brought back together. A change in the relative path lengths alters the combined light pattern. The instruments are sensitive to changes much smaller than an atomic nucleus. That sensitivity makes them natural candidates for tests of uncertain geometry. If space-time positions fluctuate in a correlated way, the effect might appear as an unexplained variation in the interferometer signal. The difficulty is that interferometers already contain many sources of noise. The ground moves, mirrors vibrate, molecules in the equipment produce thermal motion. Light arrives as individual photons, creating quantum shot noise. Electrical systems contribute interference. Weather, vehicles, aircraft, and human activity can all leave traces. An unexplained bump in the data is therefore not enough. A proposed quantum geometry signal must have a distinctive pattern. Researchers need to predict how the noise depends on frequency, direction, arm length, and the arrangement of the instrument. They must then show that ordinary environmental and mechanical effects cannot reproduce it. The Fermilab holometer was designed to search for particular forms of correlated positional uncertainty. It used two nearby interferometers operating independently. Ordinary noise produced within one instrument would not usually appear in the other at the same moment. A genuine spatial correlation affecting both might survive when the signals were compared. The holometer reached high sensitivity at frequency above those normally used by gravitational wave observatories. It tested specific models of holographic or Planckian geometry. Its results and design placed restrictions on proposed forms of correlated position noise, but they did not test every idea described as quantum foam. No generally accepted quantum geometric signal was detected. The name holographic noise can also create confusion. It is related to the holographic principle, which suggests that the information associated with a region of space may be described using its boundary. Some researchers proposed that a limited amount of geometric information could create an uncertainty in transverse position. This was a specific theoretical proposal, not an unavoidable consequence of holography. Failing to find that noise does not disprove the holographic principle. It constrains the model connecting holographic information limits with a particular interferometer signal. Ordinary gravitational wave detectors also provide limits on broad categories of spacetime noise. Their long periods of operation and carefully studied noise sources allow researchers to search for unexplained fluctuations. The interpretation remains model-dependent. Standard low-energy quantum gravity predicts effects far below the sensitivity of these instruments, while some non-standard models predict larger signals that can already be tested. Atomic clocks provide a different type of precision. Modern clocks compare frequencies associated with transitions inside atoms. They can detect extremely small differences in elapsed time and gravitational potential. Two sufficiently precise clocks placed at slightly different heights tick at measurably different rates because general relativity says gravity affects time. A quantum spacetime model might add random variations to clock comparisons. The measured frequency could wander in a way not explained by known environmental effects. Networks of clocks could look for correlations that depend on distance, direction, or the motion of Earth. The challenge is similar to the interferometer problem. Real clocks are affected by temperature, magnetic fields, motion, electronics, and the construction of the device. Any proposed spacetime signal must be separated from these ordinary causes. Atom interferometers test gravity and quantum mechanics together in another way. They place atoms into quantum superpositions in which different parts of the atomic state follow different paths. The paths are later recombined, producing an interference pattern. If spacetime foam destroys quantum coherence, the interference may be weakened. A model could predict that the uncertain geometry records information about the path, making the alternatives less able to interfere. Experiments have maintained quantum coherence across increasingly large separations and durations. These results already rule out some proposed models of gravity-related decoherence in the ranges those models originally predicted. They do not prove that gravity has no effect on coherence under any conditions, but they show that any such effect must respect the interference already observed. Larger quantum objects could improve these tests. Molecules, mechanical resonators, and other systems contain more mass than individual atoms. Placing them into well-controlled superpositions may increase their sensitivity to gravitational effects. Researchers must also control ordinary decoherence caused by gas molecules, heat, vibrations, and stray radiation. That is a severe experimental challenge. The environment is very good at destroying delicate quantum states without requiring assistance from quantum gravity. Before blaming spacetime foam, scientists have to prevent the laboratory from breathing on the experiment. There are also proposals to test whether gravity itself can create quantum entanglement. Two small masses could be placed in superpositions and allowed to interact mainly through gravity. If they become entangled, the result may suggest that gravity can carry quantum information. Such an experiment would address the quantum nature of gravity more directly then it would test Wheeler's specific foam picture. A positive result would not show tiny wormholes forming between the masses. It would support the idea that gravity cannot be treated as a completely ordinary classical field under the assumptions of the experiment. The early universe may offer another route. If extremely small quantum gravitational fluctuations existed during the earliest cosmic stages, rapid expansion might have enlarged their influence. A pattern that began near microscopic scales could become visible in the later distribution of matter or radiation. Inflationary cosmology already uses a related mechanism. Quantum fluctuations in fields during an early period of accelerated expansion can be stretched to astronomical sizes. These fluctuations later contribute to the formation of galaxies and large-scale structure. A quantum gravity effect could add a small correction to the patterns found in the cosmic microwave background or in primordial gravitational waves. Researchers look for unusual correlations, departures from statistical symmetry, or features that ordinary inflationary models do not naturally produce. This method faces several obstacles. The early universe is not directly observable. Scientists see radiation and structure produced after many stages of cosmic evolution. Different physical processes can leave similar patterns. A proposed Planck scale signature may depend strongly on assumptions about inflation, the initial quantum state, and the transition into the later hot universe. Cosmic observations also provide only one universe. A laboratory experiment can be repeated under controlled conditions. Cosmologists cannot restart the early universe with a different setting and compare the result. They must extract statistical information from the one sky available. Black holes may preserve traces of quantum spacetime as well. The final stages of black hole evaporation, the structure near the classical singularity, and the microscopic origin of horizon entropy all require quantum gravity. Unfortunately, the strongest effects are hidden behind horizons or occur under conditions that are difficult to observe. Researchers have proposed possible signals involving modified radiation, late-stage remnants, or unusual gravitational wave behavior near compact objects. These ideas remain highly model-dependent. Ordinary astrophysical environments can imitate many unexpected signals, and no accepted observation has identified a feature as Planck-scale foam. This repeated lack of detection can sound disappointing, but it is exactly how a difficult field progresses. A proposal makes a prediction, an observation tests it. If the effect is absent, the theory must be modified or discarded. The search becomes less vague because nature has removed one option. The strongest results so far often tell us what quantum foam cannot do. It cannot blur distant sources as strongly as some random accumulation models predicted. It cannot produce large energy-dependent delays of the forms already constrained by gamma-ray bursts. It cannot add certain levels of correlated interferometer noise. It cannot destroy atomic coherence at rates that would conflict with existing experiments. These limits do not reveal the correct quantum gravity theory. They force that theory to approach ordinary physics smoothly. Whatever occurs at the Planck scale must preserve the sharp, astronomical images, stable particle propagation, accurate clocks, and quantum interference that we actually observe. Future progress may come from combining several messengers rather than relying on one signal. Light, gravitational waves, neutrinos, cosmic rays, and particles, measured in laboratories, respond to different possible modifications. A theory that explains an apparent delay in one messenger must remain consistent with all the others. Longer observations improve the ability to identify stable correlations. Better telescopes increase the range of photon energies and cosmic distances available. More sensitive quantum sensors can test smaller gravitational effects. Space-based instruments can avoid some forms of ground vibration and use longer measurement paths. None of these methods guarantees a discovery. Standard quantum gravity effects may remain too small for direct observation at accessible energies. The deepest structure of space-time could be arranged so that its low-energy consequences are almost completely absorbed into the familiar laws of physics. There is also a chance that the first useful trace will not resemble foam at all. It may appear as a relationship between information and area, a limit on the precision of clocks, an unexpected pattern of entanglement, or a correction to black hole physics. Wheeler's visual language may guide the question while the answer arrives in a different form. For the moment, the universe behaves as though space-time is smooth, across every scale that has been directly tested. Light from distant galaxies remains coherent. Relativity continues to pass demanding tests. Quantum systems preserve interference when ordinary environmental noise is controlled. No observation has been accepted as evidence of quantum foam. Broad reviews of quantum gravity phenomenology therefore treat current measurements as constraints and search strategies rather than as a confirmed detection of Planck scale structure. That situation leaves two possibilities open. The foam may exist but hide its effects with extraordinary efficiency. Or the final quantum description of space-time may not resemble foam closely enough for the usual searches to find it. To decide what the phrase means after all these qualifications, we have to return to the original question. We need to separate the memorable image from the physics it represents, identify the claims that are well motivated, and admit which parts remain unknown. That brings us back to the question we started with. What is quantum foam really? The most accurate answer is that quantum foam is a name for the possible quantum structure of space-time at extremely small scales, especially near the Planck scale. It is not a confirmed substance. It is not a layer of bubbles underneath atoms. It is not a material that fills empty space. It is a way of describing the expectation that smooth classical space-time may stop being an exact description when gravity and quantum mechanics become equally important. At ordinary scales, space-time behaves smoothly. We can measure distances, compare clocks, track planets, and calculate the paths of light. General relativity describes this large-scale geometry with remarkable accuracy. The theory allows space-time to curve, stretch, and carry gravitational waves, but it still treats the geometry as continuous and definite. Quantum mechanics changes the meaning of definite. A quantum system can contain several possible outcomes. Physical quantities can fluctuate. Even the lowest energy state of a field is not completely inactive. If gravity is part of nature, and if gravity is described by space-time geometry, then it is reasonable to expect that geometry must also follow quantum rules. This is the central idea behind quantum foam. The geometry of space-time may have uncertainty. Distances may not remain perfectly defined. Curvature may fluctuate. Different patterns of connection may contribute to the same quantum process. The stable space-time around us may be the large-scale result of this deeper behavior. The word foam came from John Wheeler's attempt to imagine what geometry might be like near the Planck scale. He expected quantum gravitational fluctuations to become strong there. Space might develop temporary handles, tunnels, or other changes in connection. Small regions might behave in ways that have no simple classical description. Wheeler was not reporting something seen through an instrument. He was developing a physical picture based on the known conflict between quantum theory and gravity. His image helped physicists ask better questions. It did not provide the final answers. That distinction is worth keeping in mind because quantum foam is often presented too confidently. An illustration may show bright bubbles, tiny wormholes, and miniature black holes filling an otherwise dark space. The image can make the idea easier to remember, but it should not be mistaken for a photograph of reality. There is no known viewpoint from which someone could stand outside space-time and watch it bubble. There is no ordinary background containing the foam. If space-time itself is fluctuating, then the distances, locations, and durations used to describe the fluctuations are also part of the problem. This makes quantum foam different from familiar kinds of foam. Soap foam is made from liquid films surrounding pockets of gas. Sea foam is made from water, air, and other materials. Both exist in space and change over time. Quantum foam, if it exists, would concern the structure that gives ordinary space and time their meaning. Even the word tiny can be misleading. We usually imagine a tiny object as something with a small size located somewhere. A Planck scale geometric feature may not have one exact position in a classical space. It may be part of a quantum state in which the geometry itself is uncertain. The same caution applies to tiny wormholes. Some quantum gravity calculations include geometries with additional connections between regions. These are sometimes described as wormholes appearing and disappearing. That does not necessarily mean a complete tunnel forms at one location, stays open for a short time, and then closes. The wormhole may be one possible intermediate geometry among many. It may contribute to a calculation without becoming an independently observable object. There may be no meaningful moment when someone could point toward it and say that it definitely existed there. Virtual black holes require similar care. They are not confirmed populations of miniature astronomical black holes. They are theoretical configurations that may occur in descriptions of strong quantum gravitational fluctuations. Their exact meaning depends on the framework being used. The classical definition of a black hole assumes a definite spacetime and a clear causal structure. Near the Planck scale, those conditions may fail. A possible geometry might contain a temporally trapped region, while another possible geometry does not. Calling the first one a virtual black hole is convenient, but the name should not be allowed to make the situation sound more classical than it is. The safest description is that quantum foam represents uncertainty in geometry, and possibly topology, near the scale where our current theories stop working separately. Everything beyond that depends on the model. Some theories allow topology to change, others keep topology fixed. Some describe space-time as discrete, others treat it as continuous but quantum. Some suggest that space-time is not fundamental at all. String theory begins with extended quantum objects, and includes gravity through one of their possible vibrations. In this framework, interactions become less sharply concentrated than they would be for point particles. Geometry can change, additional dimensions can be involved, and a smooth spacetime may emerge from a deeper description. Loop quantum gravity begins by quantizing geometry more directly. Areas and volumes can take discrete quantum values. The resulting structure is not a regular grid placed inside space. The network helps define space. Causal set theory begins with events and their causal relationships. Causal dynamical approaches build large spacetime histories from simpler pieces. Holographic models connect geometry with patterns of quantum entanglement in a theory defined with fewer spatial dimensions. These programs do not give one shared picture of literal foam. What they share is the conclusion that classical smooth spacetime is unlikely to remain fundamental at every scale. The final theory may show that Wheeler's picture was surprisingly accurate. It may contain microscopic changes in connection that deserve to be called foam. It may instead show that the word was a useful early approximation, rather like describing atoms as tiny solar systems. The old picture may capture one important feature while missing the actual mechanism. Atoms are not miniature solar systems, but the comparison once helped people understand that matter contains internal structure. Quantum foam may play a similar role. It tells us that apparently empty space-time may possess a deeper structure, even if the final description looks nothing like bubbles. What can we say with greater confidence? We can say that general relativity is a classical theory. It does not include a complete quantum description of its own gravitational field. We can say that quantum mechanics applies to matter and the other known fields with extraordinary success. We can say that matter and energy affect space-time geometry. We can therefore say that situations involving strong gravity and quantum uncertainty require a theory that includes both. We can also say that the Planck scale marks the range where this combination is expected to become unavoidable. It is formed from the constants associated with gravity, quantum physics, and relativity. It does not prove that nature contains the smallest block of space, but it provides a strong guide to the scale where familiar concepts may need replacement. Beyond these points, our confidence becomes more limited. We do not know whether space is fundamentally discrete. We do not know whether topology fluctuates freely. We do not know whether tiny wormholes are genuine physical contributors in the final theory. We do not know whether time remains fundamental. We do not know which current approach to quantum gravity, if any, gives the correct description. That uncertainty is not a weakness that should be hidden. It is the current state of the science. Quantum foam sits near the boundary between well-established reasoning and unfinished theory. The motivation is strong. The direct evidence is not. No experiment has detected quantum foam. No telescope has observed a confirmed loss of image quality caused by Planck scale geometry. No interferometer has found a signal accepted as quantum spacetime noise. No particle measurement has shown an energy-dependent change in the speed of light that requires quantum gravity. Experiments have still made progress. They have ruled out or restricted several proposed effects. Distant astronomical images remain too sharp for some simple models. Gamma-ray signals place strong limits on certain energy-dependent delays. Interferometers have not found particular forms of correlated geometric noise. Quantum systems preserve coherence more successfully than some speculative models predicted. These results tell us that if spacetime has a quantum texture, that texture must hide itself very effectively at ordinary energies. This should not be surprising. The Planck length is so much smaller than any directly tested distance that a large visible effect would be difficult to explain. The deeper theory must recover the smooth spacetime already measured with great precision. A useful comparison is the air in a quiet room. At the molecular level, the air is active. Molecules travel in many directions, collide, rotate, and exchange energy. At the scale of your body, the same air feels calm. Its microscopic motion appears as stable pressure and temperature. The comparison does not mean spacetime is made from molecules. It shows how a restless microscopic description can produce a smooth, larger world. Quantum foam could be hidden because an enormous number of small possibilities combine into one stable classical geometry. Another comparison comes from a solid table. The table feels continuous and firm. At a deeper level, it contains atoms, empty regions, electromagnetic forces, and quantum states. The large-scale property of solidity emerges from those ingredients. Calling the table solid is not wrong. It is the appropriate description at the scale where hands, cups, and sleepy elbows interact with it. In the same way, calling spacetime smooth may remain completely correct for almost every practical purpose, even if a deeper description replaces smooth geometry near the Planck scale. The existence of a deeper theory does not make familiar physics an illusion. General relativity would remain valid within its domain, just as fluid mechanics remains valid even though liquids are made from molecules. The new theory would explain why general relativity works and where its limits appear. This matters because phrases such as space-time is not real can easily create confusion. A property can be emergent and still be physically real. Temperature is emergent from molecular motion, but a hot stove remains an unhelpful place to rest a hand. Sound emerges from organized motion in a medium, but it can still wake someone in the next room. Space-time may emerge from quantum relationships and still govern the motion of planets, clocks, and light. Fundamental does not mean real, and emergent does not mean imaginary. The same applies to distance. A distance may arise from a deeper network of relationships rather than existing as a basic ingredient. Once it emerges, it can still be measured reliably. Your bed does not become less supportive because its dimensions may have a quantum explanation. Quantum foam also does not mean that everyday reality can change randomly according to thought or expectation. Quantum uncertainty follows strict mathematical rules. It does not allow any outcome someone happens to prefer. A deeper quantum geometry would still have to produce stable causal relationships and the highly regular world we observe. It would not explain missing keys by placing them through a temporary wormhole. The more likely explanation remains that someone left them in a coat pocket and then blamed the structure of reality. Quantum gravity has enough problems already. The real importance of the idea is that it changes the status of space-time. Classical physics often treats space and time as part of the basic framework used to describe everything else. Quantum foam suggests that this framework may itself need an explanation. Space may have microscopic degrees of freedom. Geometry may possess quantum states. Time may arise from correlations among physical systems. The connection between two regions may be determined by entanglement or causal structure. Smooth space-time may be one phase of something more basic. This makes the search for quantum gravity different from discovering another particle. A new particle would appear within space-time and interact with other fields. A theory of quantum spacetime may explain how the setting containing particles and fields comes into existence. The task is similar to explaining the screen while every available observation appears on that screen. Physicists must use clocks, rulers, light, and matter to investigate the structure that allows clocks, rulers, light, and matter to have locations and histories. That circular difficulty is one reason progress has been slow. Experiments are hard. The required energies are enormous. The mathematical frameworks are demanding. Familiar ideas about measurement may need to be changed. Still, progress does not require immediate access to the Planck scale. Black holes provide clues through entropy and information. Cosmology may preserve traces from early high-energy conditions. Holographic models show how geometry can emerge from quantum systems and controlled examples. Precision experiments continue to remove incorrect possibilities. The final answer may come from several directions at once. A mathematical theory could explain black hole information. An astronomical observation could reveal a small departure from ordinary propagation. A laboratory experiment could show that gravity carries quantum information. Together, these results might identify the underlying structure more clearly than any one measurement could. Until then, quantum foam is best understood as a careful warning. It warns us not to assume that smooth space-time continues without change to arbitrarily small distances. It warns us that geometry may need a quantum description. It warns us that words such as location, duration, and connection may have limits. It also warns us not to mistake a helpful image for an observed fact. The foam is not the answer to quantum gravity. It is a name for the kind of behaviour that may appear when the answer is found. Perhaps the final theory will show a highly fluctuating geometry filled with temporary connections. Perhaps it will show a quiet network whose collective behaviour only looks foamy from a classical viewpoint. Perhaps space and time will emerge from information in a way that makes the original image unnecessary. Whatever the result, it must explain the calm surface we experience. It must account for why the space beside you remains stable, why the room does not lose its shape, and why light travels from one side to the other without visibly stumbling over the Planck scale. Take another look at that space now. Nothing appears unusual. The distance to the nearest wall seems fixed. The objects around you remain where they were. A clock, if one is visible, continues to mark ordinary seconds. That ordinary behaviour is not separate from the mystery. It is one of the main things the deeper theory must explain. The greatest challenge is not only describing what happens at the smallest scale, it is showing how that hidden behaviour becomes the reliable world around us. We began by looking beneath atoms, particles, and empty space. We found that the word beneath becomes less useful once space itself is being questioned. Quantum foam is not located under the universe. It is a possible description of the universe when the smooth idea of location no longer applies. We followed the idea to the Planck scale, where quantum uncertainty and gravity meet. We saw how Wheeler turned that conflict into the image of fluctuating geometry. We considered wormholes, virtual black holes, and changing connections. We looked at the larger problem of quantum gravity and at the experiments searching for traces. The result is less dramatic than a picture of endless cosmic bubbles, but it is more accurate. Quantum foam is a well-motivated possibility, an incomplete theoretical picture, and a reminder that space-time may have a deeper quantum origin. It may be real in something close to Wheeler's original sense. It may survive only as a useful historical name. At present, physics does not know. There is no need to force the uncertainty into a tidy conclusion. Some scientific questions remain open because nature has not yet supplied enough evidence. A good explanation should make the unknown part clearer, not cover it with confidence. For now, smooth spacetime continues to describe the world with remarkable success. The hypothetical foam remains far below direct observation, where gravity and quantum mechanics wait for a shared language. If this long investigation has helped you relax, you can leave a like, subscribe, or share it with someone who enjoys quiet science. You might also leave a comment with the idea that stayed with you most. Perhaps it was the Planck scale, the uncertain geometry, or the possibility that space itself is not fundamental. Wherever you are listening from, the room around you is still doing an excellent impression of perfect smoothness. The clocks remain dependable, the distances remain familiar. Whatever space-time may be doing at its smallest scale, it has been considerate enough not to disturb your evening, so allow the unanswered questions to remain unanswered for tonight. There will be other experiments, other theories, and other attempts to understand the structure beneath the smooth world we measure. For the moment, there is only the steady space around you, the slow passing of ordinary time, and the possibility that far beyond our present reach, reality is built in a way we're only beginning to understand. Sleep well, and let space-time take care of its own geometry until morning.